Okay.
Okay, thank you. Good morning, good afternoon, and good evening. My name is Chang Zhang, and then today I will, together with my colleague Vadim Makarov, to chair the first two sessions for today. And then we are very glad to chair the first experimental session. And then for this session, we have 5 speakers, 4 talks. The third talk will be merged by 2 talks, and then each speaker will have 5 minutes to talk about their research, and then after all, we will have the Q&A session for about 10 minutes. After that, all sir can go to the meet and greet room to discuss for further discussion. But meanwhile, if you want to ask question, I would strongly suggest you to put your question in the Q&A session. My colleague Vadim Makarov will check this one and then ask for you to the speaker. And then if there still have time, except for the question in the Q&A, and then you can raise your hand, and then we can ask you to, we can unmute you, and then you can ask question. Okay, so I think it's clear. Then we welcome our first speaker, Wei Li and Feihu Xu from University of Science and Technology of China, Jiangpan Group. And he'll talk about high-speed MDI-QKD with silicon photonics. Wei, please.
Okay, thanks. Hello, everyone. This is Wei Li from the University of Science and Technology of China. I want to talk about our recent works on high-speed MDI-QKD with silicon photonics, featuring gigahertz implementation together with the integration of the transmitter in our measurement device independent system. Let me give you an idea of our motivation. QKD links can only operate over point-to-point connection between two users, thus cannot be deployed over any arbitrary network topology, and is distance limited. So far, the existing QKD network implement trusted relays to extend the reach of QKD links in a hop-by-hop fashion. More recently, a network-centric or quantum access network is proposed in a way that a quantum receiver works as a server for many users, which is suitable for metropolitan network. Nonetheless, it's also based on a trusted relay. In the future, the implementation of untrusted relays can be a huge security upgrade to the network. In the development of QKD network, QKD systems have gone from tabletop experiments to compact and autonomous system and now growing commercial market. Thanks to the emerging nanophotonics technology, QKD systems are enabled to be integrated onto a chip. There are some pioneering works demonstrating various QKD protocols recently. Among them, silicon and indium phosphide are two promising platforms. The silicon has a mature industrial production chain, and some company like IMAC provides commercial solution to the users like us. Due to its advantages of compact size and low cost, it's reasonable to envisage that the system integration is inevitable for future developments. By replacing the quantum receiver with a Bell state measurement device, and each user holds a transmitter chip, the network-centric structure with an untrusted relay is enabled by the combination of silicon photonic chips and MDI-QKD. The introduction of MDI-QKD can remove the detection loopholes, which are a huge improvement considering the detection site is the weakest spot. What is even better is that the relay holds the expensive and bulky measurement device, which is shared by all users. And this structure can bypass the challenging techniques of integrating single photon detectors onto the chip, as the user do not need to perform the measurement. Overall, the chip-based MDI-QKD network enables a promising solution for low-cost, scalable QKD network with an untrusted relay, which has not been demonstrated yet. As a first step, we experimentally demonstrate a 1.25 gigahertz polarization encoding MDI-QKD system with silicon photonic modulation chip. As shown on the right, the chip integrates the QKD encoding components of intensity modulator, a polarization modulator, and three-stage variable optical attenuators. Paired with a dedicated driving circuit, we have successfully produced randomly modulated polarization states with a 23 dB extinction ratio at gigahertz operation. To operate a MDI-QKD system faithfully at gigahertz, we face two experimental challenges. First, a carrier depletion modulator on silicon substrate has a large half-wave voltage, which is 5 to 6 volts. We designed an FPGA board to output 4 independently adjustable levels at 10 gigahertz sampling rates and then amplify to 7.5 volts. Second, a good interference between 2 independent lasers are crucial for MDI-QKD. Gigahertz operation is not an easy task. We leverage the injection locking technique and an extra optical filter to minimize the time jitter and the frequency chirp. Using the described setup, we perform a series MDI-QKD experiments using the 4-intensity decoy state protocol proposed by Xiangbin Wang. In the finite key scenario, we perform a full optimization of the parameters by exploiting a joint constraint for the statistical fluctuations. We obtain 268 bits per second secret key rate over 28 dB loss channel, and according to the simulation results, we achieved the highest key rates among the reported MDI-QKD experiments. To summarize this talk, we experimentally demonstrate a 1.25 gigahertz chip-based silicon photonic transmitter chip. The transmitter can be further integrated with the laser based on wire bonding or hybrid integration. We perform a complete demonstration of the polarization encoding MDI-QKD and distill finite key rates higher than the previous experiments. This work paves the way for low-cost wafer-scale manufactured MDI-QKD system and represents a key step towards building QKD network with untrusted relay. And thank you for your attention.
Okay, thank you, Wei. You control your time very well. And then before our next speaker, I would like to say that if you put your question in the Q&A, please specify which speaker you want to ask. That'll be easier for Vadim and I. So then let's go to our next talk. Qin, could you share your screen? Our next speaker is Qin Wang. She's a professor from Nanjing University of Post and Telecommunication. She will talk about experimental MDI-QKD with uncharacterized sources. Okay, Qin, please.
Okay. Hello, everyone. It's my pleasure to present our recent work in QCrypt. My name is Qin Wang. I'm from Nanjing University of Post and Telecommunications. Here is our website. You're welcome to visit us. Here is the outline of my talk. For time reason, I will only briefly introduce the background, the protocol, and the experiment, finally concluding the game out. Okay, now let's see the background. As we know, there always exist conflicts between theoretical uncontinuous security and the practical setup of quantum bouquet distribution, because in reality, we only have imperfect light source, imperfect encoding device, and imperfect single-funnel detectors. According to those imperfections, the eavesdropper may carry out different kind of attacking strategies, like listed here, and thus threaten the security of practical quantum bouquet distribution. How to resolve them? People put forward a different kind of method. For example, the decoy step method. Has been put forward to solve the photonom splitting attack, and the main device independent QKD protocol has been invented to show all the side channel attacks directed on the main part. However, most of them still has some assumptions. For example, it needs perfect state preparation. We know it's impossible to have perfect state preparation in practice. Then people give out different protocols, like a loss tolerant protocol by Tamaki Ito and the uncharacterized source protocol by Yin Ito. They both take source security into account and thus increase the practical security of QKD. And our present work mainly focuses on the second protocol, unauthorized source protocol. Since the first unauthorized protocol by Ying gives very low key rate, ran in 2017, Huang et al. Derived a multi-titan bond for the phase error rate, and thus increased the key rate, but they consider only the ideal synchronous source. Based on Huang and Ying et al.'s work, we put forward a practical scheme on MDI-QKD with uncharacterized source. Here, Alice and Bob, they use weak coherent source and randomly prepare them in 3 different kind of intensity and 2 bases. It's listed here, and then send it to the third party, Charlie, for first state measurement. Notice the main difference between standard MDI-QKD and the one with uncharacterized source. On the left, it represents the standard MDI-QKD, and on the right, it corresponds to the one with uncharacterized source. Firstly, on the left, it assumes almost perfect state preparation. On the right, all the encoding device, all the encoding states don't have to be idle states. The only exception is they are located in 2-dimensional Hilbert space. Secondly, it needed to prepare 4 states in 2 bases on the left, while on the right, it only needed to prepare 3 states. Typically, in X bases, it only needed to prepare 1 state. Thirdly, on the left, Alice and Bob will keep all the successful events from matched bases, while on the right, they will keep all the successful events from both matched or mismatched bases. Here is the schematic of our experimental setup. This is Alice, Bob, and Charlie. For time reading, I won't speak too much about the experimental detail. You can find them on the video on the website made by my student Xingyu. I only introduce the experimental result here. As shown in this figure, the red line and the red points are our corresponding to our theoretical and experimental results. We can see they agree well with each other. The black line, the blue, and the green points are from the reference below. They either use loss tolerant protocol or use uncharacterized source protocol. They possess similar security level as ours, but as we can see, our experimental and theoretical results greatly extend the performance compared with other existing work. In conclusion, we put forward a practical scheme on decoy state MDI-QKD with 3 uncharacterized states, and realize experimental demonstration with a transmission distance up to 170 kilometers, which represents the longest transmission distance when considering source security. Here is our team. And thank you for your attention.
Okay, thank you, Qin. And then our next speaker is a merge talk by it was given by Luca Caldararo and then Castanino Axi from University of Padua, Paulo Villorosi group. So please.
Yeah. Okay. Thank you, I'm Luca Calderaro, and together with Costantino Agnesi, we would like to thank, first of all, the organizers for letting us presenting our work to this conference. So our works are based on this. Okay, I can switch. Our works are based on the following consideration. So we believe that the widespread deployment of QKD in our current telecommunication networks will require the development of simpler and more robust systems. So with this in mind, we developed a QKD system which is able to perform the synchronization and the polarization compensation by exploiting only the hardware already needed for the quantum communication tasks. So we introduced a synchronization method that we call QBit4Sync that I will talk about in the next slide. We also use a predetermined qubit sequence exploited to monitor and compensate the polarization drift of the quantum channel. We use a polarization encodings with a self-compensating POGNAC scheme, which is based on a Sagnac loop. And Costantino will talk about it in more detail. And we put it together to implement a three-state, one decoy efficient BB84 protocol, which was introduced by Grunfelder and others. So QBit4Sync is a software-based synchronization method which uses only the qubits exchanged during the QKD protocols. So the signal frequency of the qubits is calculated via a frequency analysis using the time of arrivals of the qubits, while the time offset between the receiver and transmitter clocks is calculated via cross-correlation of a public string, which is prepended to the random string of Alice. And in doing so, we introduce a novel fast cross-correlation algorithm with a computational complexity of L log L, where L is the length of the synchronization string. So we saw that this method is robust to high Q-bar, and also it can be adapted to the channel losses by tweaking the length of the synchronization string, so that the higher the channel losses, the longer it needs to be the synchronization string. The advantages of this approach is that the data throughput is maximized, as any physical channel can be exploited for data stream, and the hardware for an external synchronization service is not required. So this means gaining in simplicity and robustness of the system. And as a final remark, we think that this method may be also used in other quantum communication protocols, such as quantum direct communication or quantum bit commitment. And with this, I leave the stage to Costantino Agnesi.
Thank you, Luca. So as you mentioned in the introduction, for our experiment, we developed a polarization encoder, which we named the POGNAC, which is based on a Sagnac interferometer. And this self-compensating design allows it to have a quite impressive long-term stability. Could you go back, Luca, please? Yeah, okay, thank you. Thermal and mechanical drifts are in fact compensated by this design. Furthermore, it only requires a standard phase modulator that is then converted to a polarization modulation. And this, in fact, allows this design to be easily implemented both at 1550 nanometers as well as, for example, 800 nanometers using commercial off-the-shelf components exclusively. Furthermore, it requires a low VUPI voltage compared to other inline polarization modulators. And lastly, it has no polarization mode dispersion, which allows us to have an extremely low quantum bit error rate. In fact, we tested our system and we obtained 33 dB of polarization extinction ratio. And this is the lowest intrinsic quantum bit error rate ever reported in the scientific literature. Next slide, please, Luca. Putting all these things together, we developed our QKD system, where we have a base clock of 15 megahertz, and our light is emitted at 1550 nanometers. Then we have an intensity modulator and the POGNAC polarization modulator to implement the simplified one decoy, three polarization state BB84 protocol. After which we have a quantum channel that is composed of a 26 kilometer fiber spool, followed by a variable optical attenuator, which allows us to emulate further channel losses. And then we have the receiver, which is completely composed of commercial off-the-shelf components for the polarization state analysis. And then we have a superconducting nanowire detectors, as well as a 1 picosecond time to digital converter at the detector. And using this setup, we tested our system for several channel losses. And well, for a synchronization key length of 10 to the 6, we managed to obtain about 34 dB of losses for a system to fully work. And we had to increment the synchronization string length to 10 to the 7, with which we managed to run QKD protocols with the qubit for sync synchronization up to the losses at which the key rate drops to 0, which is approximately 41 dB. And at 40 dB of channel losses, we obtained 80 bits of secure key per second. Now, as the conclusions, we demonstrated a simple quantum key distribution system which has reduced hardware requirements. In fact, we use the same setup for 3 different tasks. We do synchronization, polarization compensation, and quantum communication with the same hardware without requiring any changes or additional hardware of our setup. We developed a polarization encoder which exhibits a record low intrinsic quantum bit error rate, and we managed to obtain relatively high secure key rates and high resilience to channel losses, even with only 50 megahertz repetition rate. In conclusion, the reduced hardware requirements and the quality of the source represents this work an important step towards technologically mature quantum key distribution systems.
Okay, thank you, Luca, and then Costantino. So let's go to the last talk of the session. It's given by Robert Starek from Harold Walt University with Erica Anderson. Yes, please, Robert.
Okay, can you hear me? Good, good. So thanks for introduction. Our work is about experimental realization of quantum oblivious transfer. Here are mainly QKD experts. So first, let's introduce this idea briefly. So in this communication task, Alice has 2 bits, x0 and x1, and she would like to send them to Bob. But Bob can only receive a single bit based on his choice C. Here C equals 0, and the other bit, here x1, should be discarded and Bob should not know its value. Similarly, Alice is not allowed to know Bob's choice. We will discuss so-called semi-random OT, which is very similar up to the detail of the bit C, because now Bob doesn't choose at will, but rather bit C is randomly generated. This communication primitive is very useful for secure multi-party computation, and but unfortunately we know that it is impossible to do this task perfectly, both in classical and quantum setting. We know that the theoretically most secure protocol you can get has 66% of cheating, which means that Alice or Bob can correctly guess what should remain hidden in 66%. On the other hand, the best known protocol we know today has 75% cheating probability. Improving the protocol would mean reducing the cheating probability down to the 66%. So specifically, we came with a new protocol for semi-random oblivious transfer, which is based on an ambiguous measurement. It is very simple. Alice only encodes a qubit or pair of qubits based on her choice. Then she sends the states to Bob, and Bob does measurement in ZX basis. From this measurement, he can obtain the choice C and the corresponding value of bit XC. So this protocol can be cheated with 75% cheating probability. It's the same as the best currently known protocol, but the advantage, I think, is that this protocol is compatible with BB84 setup. So if you have in the lab BB84, if you can transfer qubits and then classical communication, then you can also run this protocol. And this semi-random protocol is equivalent to a regular oblivious transfer protocol. Only extra you need to do is few rounds of classical communication to clarify what is the result. So let's go very quickly to the experiment. So we did a proof of principle experiment. We used a single photon and we encoded 2 qubits on it in polarization and path here using simple wave plates and calcite beam displacing crystal. And then we basically sequentially prepared all of these 4 states. And for each of those states, we measured all projections of interest. So this is the illustration of the typical results or like ensemble of the results. So in this case, both parties were honest, no one was cheating, and Bob could obtain the bit correctly in more than 99% of the cases. Okay, then we tested also cheating strategy, which is also straightforward for Bob. He only needs to do quantum state discrimination. So instead of measuring in Z and X bases, he uses zeta and Xi bases, and he can cheat in 73%. And the cheating Alice, it's the last slide. It's more difficult because it involves creation of such entangled state, which basically is a entangled superposition of valid protocol states. And then Alice can cheat with 75% probability in theory. Here she cheated more often, but it comes of the cost that she gets revealed sometimes. So time's up. So thanks for your attention. And if you are interested, please check our archive paper or see the full video, and then meet me in the meet and greet room. And I would be happy to answer your questions. Thanks. Thanks.
Okay, now is Vadim's your time to chair the session.
Thank you very much. I have some questions. So the first question is to Shin.
Vadim, your voice is a little bit sticky.
Okay. Sorry, I have reconnect. This is my connection.
Okay, since Vadim reconnected, so I probably first chair the session for him because of limited time. We already a little bit delayed, so we want to extend the time. So, but anyway, I'll first.
Is it better now?
Good.
Okay.
Go ahead.
Sorry, man. Oh shit! I'm sorry. I lost all the questions because my chat cleared when I exited. Shan, can you please handle the questions? There was a question to Shin. Can you read it, please?
Yeah, Chin, can you read that? It's from Mohsen Razavi. Let's work. If I understand your protocol correctly, you mentioned that you assume that the source only generates two-dimensional states. So question 1, how do you make sure this is the case? And the question 2, doesn't this contradict with the use of decoy state, which are infinite dimensional in number state basis? You can also read the question in the Q&A, yeah.
Yeah, let me answer this question. In fact, these two questions have some relations. I answer the first I answer the second question. It has no confliction with the decoy state method because the decoy state method is just to bound the single photon contribution, right? When you decoy state to bound the single photon state is secure, then we come to the assumption the single photon state, the encoding information on the single photon source only lie in two-dimensional space. That means there is no high-dimensional side channel links. For example, when we encode when encoder state in phase space, there will no side channel links in polarization or some other dimension space. Do I answer your question?
Well,
Okay.
yeah. Vadim, can you see the question for
Yes.
Constantino?
The next question is to Konstantina. For the loop polarization encoder, it might have problems for high-speed polarization encoding because the pulses are quite close in time. What is the limit of the repetition rate for your encoder?
Yes, so we have tested our polarization encoder up to 100 megahertz without any issue. But I know of other groups that have similar architectures for intensity modulation that have managed to implement repetition rates up to 1 gigahertz or maybe a bit above 1 gigahertz. So yeah, we would expect for our system to work also at the maximum 1 gigahertz, which is basically limited by the speed of the electronics that we have.
Okay, there was a question to Wei. How big is the entire transmitter module, including the master and slave lasers?
Okay, so the final form of our transmitter, both the optical module and the electronics are soldered onto the PC printed circuit board, the laser can be further integrated onto the chip without the injection seating setup. So, and it has been demonstrated on silicon and indium phosphide substrate by, I think, Bristol group and Padova group recently, and both demonstrate a very good homomandal visibility. So I think the integration of the laser and the transmitter and the modulation components is not a big question. So, thank you.
I have a follow-up question. How much does it cost to produce this integrated chip when done in quantity?
Sorry, can you repeat your?
What is the cost of manufacture for the chip? If you do it in a large quantity, the order of?
The cost of the fabrication of the chip, right?
Yes.
So we handle our design to the production to the company IMAC. So I think the cost for the fabrication is over $100K, but the chip can be produced repeatedly. So if you want to produce 1,000 chips and 10 chips, the cost is not much difference. Okay.
Does the public have questions? If not, I can ask a question to Konstantina. Konstantina, how do you do polarization compensation? How do you compensate the drift of polarization in the transmission line in your scheme?
So you mean at the transmission, the polarization drift between Alice and Bob, you mean?
Exactly.
So what we do is we use the same concept as qubits for sync. So we have a public shared string, and at the beginning of each second, we measure the Kubert of that string without having to reveal other data. So immediately after we estimate the Kubert, we have automatic polarization controllers that apply a change to the polarization state, trying to minimize this quantum bit error rate. This is simplified explanation of what we basically do.
Vadim, I have a question for the last speaker, Robert. Can I? Okay.
Yes.
Hi, Robert.
Hi.
Do you? I want to know the exact kind of assumption between your protocol and with the real oblivious transfer. Could you explain in a little bit more detail? And what do you think? Do you think it can have some application or not? Thank you.
Yeah. So let's start with the latter question. This is actually an open question because we know we cannot use it perfectly, so it cannot be relied onto as a plug and play block. But for me, it's still interesting whether if there is some limited cheating probability, whether you can still use it. So basically, I think this is actually a question for experimentalists. Sorry, for theorists, whether you can find a protocol or task in which you can use the oblivious transfer even with limited cheating probability. Then the question which is open and perhaps would be very interesting to investigate is whether when you have limited quantum abilities, like limited quantum memory, whether you can design a new protocol that would be very secure if you allowed these assumptions, or I don't know, finite quantum memory time and finite efficiency, finite fidelities of your gate, and so on. And could you please repeat the first part of the question? I should compare the presented scheme with Yao's.
With the true oblivious transfer. I think you did some assumption, right, for your protocol?
Actually, it doesn't have. So perhaps it would be best if I review the assumptions in our protocol. So, or what we considered, and or what we did not consider. So actually, we did not consider a third party. So we didn't consider any eavesdropper, and we did not consider any loopholes like detector blinding and detector losses. And of course, these things have to be treated because I can easily imagine that you can use detector blinding to trick Bob into whatever value you want. And I can easily imagine Bob faking losses and requesting Alice to repeat to obtain enough samples for qubit tomography and then knowing both bits perfectly.
Thank you.
Okay, thanks.
I think we have to stop here to give time for the next session.
Right, thank you very much to all the speakers. We'd like to invite you to move over to the meet and greet room and take your seats so people can go there and ask you more questions in case. And the next session will start in, well, almost 5 minutes actually. I think we'll just have the webinar open.
I have one question. Which floor I should go?
There's an announcement board in the if you enter, there you can see your
We leave. Welcome to the second session for today. I'm Vadim Makarov. I will chair the session, and my colleague Shan Zhan will handle the questions and answers. If you have questions to the speakers, please type them in the Q&A box in Zoom. I pass the podium to Ernst Tan for the first presentation.
Okay, thank you. Okay, So good morning or afternoon, everyone. So today I'm presenting a result on improving the robustness for device-independent QKD. This is a joint work with some collaborators from the Center for Quantum Technologies in Singapore, as well as the Leibniz University, Hanover. So device-independent QKD is based on the observation that if you have a violation of a Bell inequality, then in fact you can prove the security of, say, QKD without having to trust that the measurements are being performed in the expected manner. So it's possible to construct a security proof where you don't trust what measurements the devices are performing. So this helps to reduce the number of assumptions in the security proof, which may also help to reduce the attack surface on the protocol. However, the drawback of this stronger sounding form of security is that there is less noise robustness for the known security proofs. So currently the known DI-QKD protocols, they are not very robust against noise. And because of this, we don't really have a full experimental demonstration of DI-QKD at this point. The main point of this work is a modification to DI-QKD protocols such that we can improve their noise robustness. And the key observation that we use in this work is essentially this trick here, which is that for many of the standard DI-QKD protocols, you mainly use one of the measurements for key generation. So for instance, Alice's measurement A0 is the one that's mainly used for key generation. But if we think back to the earlier QKD protocol proposals, quite a number of them were based on sifting, in the sense that you pick your basis choices uniformly at random, and then you apply a sifting step at the end of the protocol. The reason why we might expect, in fact, some cases where the key rate from the sifting-based protocol is higher would be that if we consider the case where you only use one measurement for key generation, A0 here, you have to allow for the possibility of it being the worst case measurement, in the sense that it's the one that leaks the most information to Eve. On the other hand, if you use your uniformly random basis choices, then you can show that if there is any non-trivial CHSH violation, the two measurements have to be different measurements. And in particular, this means that you cannot have both of the measurements being the worst case measurement. And this is why you might be able to expect some amount of improvement from using the sifting-based protocol instead. But computing the key rate from this sifting-based protocol is a little bit challenging. We developed some approaches in this work to help tackle this task. But for the purpose of this point, I'll just quickly summarize the results that we got from our approach. So on this graph here, it's a region plot where the axes are the QBER and CHSH values from several Bell test experiments. And the coloring of this plot is that the blue regions here are where we can show that there's a positive key rate from the sifting-based protocol, where darker shades of blue refer to higher positive key rates. And the important point that we want to do is to compare this against the results for the standard protocol, which is shown in this graph here that was taken from a previous work. Although the color scheme for this graph is that the green region is where positive key rates are achieved. And for now, I will draw your attention to specifically to the Bell test experiments that are highlighted in this blue box here, because these are the loophole-free Bell test experiments. And each of these experiments is plotted as a corresponding point on this graph together with its error bars. So for the standard protocol, we can see that one of the Bell test, loophole-free Bell test experiments is just on the border of achieving positive asymptotic key rate using the standard protocol. This is experiment number 7, which is the NV Center Bell test. On the other hand, if we instead use a sifting-based protocol, our results show that this is able to achieve a clearly positive asymptotic key rate because this is clearly within the blue region. And in addition, there is another Bell test that enters the region of positive key rates, which is the one based on coal atoms. So we can see that using a sifting-based protocol, you can have at least 2 kinds of Bell test implementations that, at least in principle, achieve a positive key rate asymptotically. On the other hand, for photonic experiments, it seems like our approach doesn't manage to guarantee a positive asymptotic key rate for them. But I'll just briefly mention that for photonic experiments, there's a different approach that may be more promising. It's known as noisy preprocessing, which is a technique from standard QKD. We released a result on this a few months ago, and we are presenting it during the poster session later today, if you would like to take a look for the photonic setups. But with these results in mind, the key questions that remain to be addressed, one of the important things that we should tackle would be the finite size analysis, Because one important difference between the various bell test implementations is that they have extremely different sample sizes. So even though we can now claim that some of the bell test experiments are in principle able to achieve a positive asymptotic key rate, the sample sizes in the actual experiment may not be large enough to certify a key rate with when you consider the finite size effects. So we are in the middle of preparing the finite size analysis of these protocols, so that we can compare the different bell test implementations. As a small helpful side effect, we are also proposing a modification to the analysis that allows us to potentially remove the sifting factor, because if you have to sift out about half the rounds for mismatch basis choices, this is quite a heavy penalty to the key rate. And in addition, we are also looking into whether this approach of using uniformly random basis choices can be combined together with noisy preprocessing. So we are also currently developing this approach, and there are several other advantages available using this optimization method that we are now developing. If you would like to hear more details about it, it's described in the full talk, and I can also discuss it during the question session. And with these results in mind, well, it would be nice to try and attempt an experimental implementation of DI-QKD at this point. So we would have to look very carefully into the experimental parameters and try to optimize them for a demonstration. This is fairly challenging because there's many parameters to optimize, but we have a few ideas in mind that we are investigating. And yeah, I guess to sum up, so we have made the observation that if you use a sifting-based protocol for DI-QKD, you can substantially improve its noise robustness, and some bell test experiments may potentially be able to achieve a positive asymptotic key rate at this point. Yeah, I guess that wraps up my presentation. I'll be glad to have your questions afterwards.
Thank you, Ernest. The next speaker is Wen Zhao Liu, please.
Sorry, let me just, okay.
Can you see the slides?
Yes, please go on.
Okay. Hello, everyone. Thanks to the organizer to give me this opportunity to present our recent work, Device-Independent Randomness Expansion Against Quantum Adversary. My name is Wen Zhao Liu. I come from the USTC, the University of Science and Technology of China. This is a joint work with Professor Roger Kovac, who provides theoretical support. I and my colleagues in the USTC are mainly responsible for the experimental part. You can find more details on our archive paper. First, let me briefly introduce the random number. It can be defined from two aspects. One is that the random number needs to obey uniform distribution. The other is that it should be unpredictable, which means that it should be independent of anything else. Since random number has many applications in our lives, we have motivations to do some research. The first is to build a well-random number generator. For a classical one, its output could be well uniform, but it is predictable in principle. In the case of quantum, it is unpredictable in principle, because this is guaranteed by the intrinsic randomness of quantum mechanics. Let's come to the schemes to realize randomness generation. We just consider a simple physical model using a 50-50 beam splitter to generate a raw string. And then we estimate the amount of randomness, which should be unpredictable to adversary. Finally, we extract the uniform random bits by classical processing. However, for real devices, it is difficult to find a complete physical model that could describe all of the physical processes in a random number generator. Besides, how much randomness could be extracted from the raw string is also not an easy thing to calculate. Another motivation is to check a candidate random number generator working correctly. Up to now, we could not find any good test that only acts on the output. Based on these ideas, we found that the device-independent protocol is a good way to realize a real random number generator. The figure is a conceptual diagram of the device-independent protocol. We do not care about how it works in the black box, but only consider the joint probability of the input and output, as long as it proved to violate the Bell equality. The output must contain unpredictable randomness. This protocol can be used to check a candidate random number generator and also easy to check. Not focusing on the specific devices makes it general and could against different attacks, but difficult to experimentally achieve. Here I list the experimental demonstration of DI-QRNG. It can be found that in all demonstrations, the amount of output is much smaller than the input. Considering the need for the large amount of randomness in practical applications, DI-QRNG is not enough. Therefore, we hope to realize device-independent randomness expansion, where the generated randomness surpasses the consumed. For the DI randomness generation, in each round, the randomness consumption is always 2 bits, and the randomness generated could never more than 2 due to the correlations between A and B. In order to achieve expansion, we need to reduce the entropy consumption. As shown in the figure, we adopt the spot checking protocol to realize the net gain. We say Ti satisfy a distribution gamma and 1 minus gamma. If Ti equals 0, the input of Alice and Bob, Xi and Yi are both 0. If Ti equals 1, each unbiased random number generator will be triggered and produce random number uniformly. We could obtain the CHSH value according to the joint distribution in the test rounds. During the implementation of protocol, there is a condition related to the accumulated CHSH value to decide whether to abort. If the protocol succeeds without stop, we estimate the amount of randomness and perform extraction. This is our experimental setup. The system is located in a single lab. A is the entanglement source. The entangled photons are generated by spontaneous parametric down conversion and are delivered to measurement sites. B represents the measurement sites, Alice and Bob. Each of them uses a POG cell to project the single photon into one of 2 predetermined measurement bases, and then detects single photons with a superconducting nanowire single photon detector. In our experiment, we do not close the locality loophole. In order to satisfy the non-signaling condition, we use shielding assumptions to prevent the potential communications between Alice and Bob, and also between biased QRNG and measurement sites. We also realized randomness expansion in a separate work, in which the locality loophole was closed in the test round. The setup used the same platform, but differs in the location of Alice and Bob, who are instead at 2 remote sites. As a comparison, we analyze its performance using the same theory with the same error parameters as before. In our experiment, we use the entropy accumulation theory, EAT. By using the smooth mean entropy to estimate the amount of randomness, the EAT method provides relatively tight bounds on the amount of randomness that can be extracted against quantum adversary. For the randomness input, since we use a strong extractor, we did not take the state for extraction into account. Now let's come to the results. There are 2 figures on this slide. The figure A is the minimum number of rounds to witness randomness expansion. To better show the progress in our experiment, we made it a comparison with our previous DI-QRNG work, which is the open square in figure A. It would take at least 118,000 hours to witness expansion with our revised EAT method, which is too long in practice. The circle and cross represent the minimum number of rounds to witness expansion with our platforms. In our experiment, we achieved the expansion protocol in 220 hours for the experiment with space-like separation and 19.2 hours for our main experiment. The figure B is the randomness expansion rate versus number of rounds. Our results are represented by the cross and circle. The asymptotic rates are only decided by the CHSH value. We notice there are 2 related works. One is another work of our group with the quantum probability estimation framework, QPE. This theory was initially developed by the NIST group. They also achieved the random expansion. Please see the next talk by Yan Bao to find more details. Let me make a brief summary. We achieved the randomness expansion with the revised EAT theory and complete the experiments independently with 2 different experimental platforms. For the future, on the experiment, we plan to continue to improve the performance of our system, and we can also do some practical shielding methods to make the experiment more convincing. On the theory, maybe the EAT method could be further improved to get more randomness, and also a detailed comparison between the EAT and the QPE is also meaningful. That's all. Thank you for your attention.
Thank you, Wen Shao. The next speaker is Yanbao Zhang, please. Unmute yourself, please. You are muted.
Oh, sorry. So
now it's fine.
Can you hear me? Oh, okay. Sorry. So thanks for the introduction. Hello, everyone. I'm going to present our recent work on device-independent randomness expansion. So this work is a collaboration among several institutions. The experiments were performed at NIST, led by Crystal. High-efficient single-photon detectors were developed by Siwoo's group. The quantum random number generators used are from Morgan's group. I worked with Mohammed Honghao Mani on the theory side of this work. So first, let me briefly introduce device-independent randomness. As you already heard from Wen Zhao, so in the device-independent case, we do not need to trust a quantum device. So we model each device by a black box. The main idea is we can perform a Bell test. We can test a Bell inequality to see whether there is a violation of local realism. If there exists a violation, so the outputs of the tests are not deterministic functions of the inputs and any other set information, such as local variables. So in this case, so the outputs must contain intrinsic randomness. Since we do not trust a quantum device, so we call this device-independent randomness generation. Next, let me briefly explain what is randomness expansion. So by performing a Bell test, we get a sequence of outputs. We can certify the amount of randomness in the outputs. After that, we can run an extractor to get a short sequence of uniform bits. Over this process, we use random bits for performing the Bell tests. Also, we use the random bits for running the extractor. Randomness expansion is achieved if the amount of output randomness is more than the input randomness. As already heard from Wen Zhao, until recently, device-independent randomness expansion has not yet been demonstrated. People proposed to use the spot checking protocol to achieve randomness expansion. But for running this protocol, we use both uniform and non-uniform random bits. We use non-uniform random bits with a specific bias to decide whether a trial is a spot checking trial. In a spot checking trial, Alice and Bob just perform a Bell test. We use uniform bits to determine the inputs of Alice and Bob for the Bell test. However, in practice, it is not easy to access non-uniform bits with a specific bias. To avoid using non-uniform bits, we develop a protocol called a blockwise spot checking protocol. In this protocol, we group experimental trials into a sequence of blocks. Each block has a random number of trials. Specifically, we use key bits to choose the number of trials in a block. The last trial in a block is a spot checking trial, where Alice and Bob perform the Bell test. For the other trials in a block, Alice and Bob just use fixed inputs. Similar to the usual spot checking protocol, we can make an assumption, like the untrusted devices can't learn in advance when a block will end with a spot checking trial. In this case, we can certify randomness generated from every trail in a block. At the same time, you can see each block consumes only k bits for determining the number of trails in the block. Also 2 bits for the spot checking trail, the bell test in the spot checking trail. So it's possible to achieve randomness expansion. Next, let me briefly describe our experimental implementation. We use a loophole-free bell test configuration. Alice and Bob are far away from each other so that we can ensure their measurement processes are space-like separated. Also, Alice and Bob perform measurements with high-efficient single-photon detectors, so we can close the detection loophole. In the protocol, we also use a trusted third-party spot to determine the number of trails in a block. Specifically, Spot uses 17 random bits from a NIST randomness beacon for this purpose. We use 17 random bits according to our security analysis. Over 2 weeks, we collected enough data for expansion analysis. Our main result can be summarized into this plot. Here you can see the amount of output random bits change with the number of blocks analyzed. So at the beginning, we can't certify output randomness. After some point, the output randomness surpasses the input randomness. And after 91 hours in experiments, our success threshold was satisfied. So we successfully achieved randomness expansion. These experiments took about 2 weeks. However, it can generate much more randomness than the NIST randomness beacon in the last 3 years. With this, I would like to stop. Thank you for your attention.
Thank you very much, Yan Bao. The next speaker is Victor Zapatero.
Can you hear me?
Yes, go on, please.
So, good morning. My name is Victor Zapatero. Thanks a lot to the organizers for making this online QCrypt possible. And for those of you who didn't watch the long video presentation, this work is a collaboration between the University of Science and Technology of China and the University of Vigo in Spain. And what we do is we report on the first QKD experiment secure against malicious QKD equipment based on the use of redundant devices and distributed post-processing. The motivation behind this work is the unjustified assumption that the devices used by Alice and Bob in a QKD session are honest. And I say unjustified because our experience in classical crypto indicates so. Malware, backdoors, covert channels, and things like this are also expected to affect quantum crypto because the manufacturer of the equipment may provide if with plenty of opportunities to sabotage the devices before they reach the end users. So in the first place, I would like to comment on some unsatisfactory attempts to eliminate this honesty hypothesis. And the first one is probably DI-QKD. When talking about malicious devices, this idea may come to our minds. However, the so-called memory attacks illustrate that DI-QKD is not secure if the devices are not only faulty or uncharacterized, but actually malicious. And the fundamental weakness that remains even in the DI setting is the simple fact that the final keys are classical objects that can be copied. On the other hand, the ideal solution consists of Alice and Bob validating the integrity of their system, of every component. However, this kind of post-fabrication tests are typically very time-consuming and actually they can be evaded in practice. So, what is the main idea behind our QKD experiment? The idea is the following argument raised by Marcos Curti and Hoi Kwon Lo. Probably it is harder for you to corrupt various devices than a single device, especially if they originate from different vendors. Therefore, the parties should use a redundant number of devices and assume that a limited number of them is corrupted. And if this is the case, security can be restored by combining verifiable secret sharing and privacy amplification, which are two well-known techniques. And crucially, this is the best one can expect, because QKD will be insecure if multiple devices are compromised, not just one QKD system. And it is up to the users to decide how many corrupted devices they want to be protected against. But before I move with the talk, I would like to distinguish the two different parts of a QKD setup, which are the QKD pairs or the QKD modules, which are these two blue boxes linked by a quantum channel and are responsible for the quantum communication phase, and the CP units, which are the pink boxes linked by authenticated classical channels that implement the post-processing of the raw data into the final keys. In standard QKD, where the devices are trusted, it suffices for each party to have one device of each kind. However, if malicious devices are considered, a different setup is necessary. And the one we suggest looks like this. Essentially, it is based on redundancy. What we need is multiple pairs of QKD modules or QKD pairs and multiple CP units per lab, together with some extra classical authenticated channels. And if this is the case, security can be restored as shown by Marcos Curti and Hoi-Kong Lo with the following assumptions. At least one QKD pair is not corrupted. Less than one-third of the CP units are corrupted in each lab, and Eve is assumed to fully control all the corrupted devices. And as I said before, the tools to establish security are verifiable secret sharing and privacy amplification. And now we can see how these two tools combine. And this takes us to the rationale behind our protocol. In the first place, multiple QKD sessions take place. Okay, so in each session, a QKD pair obtains its own raw key. And then the post-processing of these raw keys starts. And here is where verifiable secret sharing comes into play. The post-processing of each key is performed redundantly to assure correctness, and the key material is divided into random shares to assure that they are kept private through the process. And crucially, the linearity of the post-processing operations makes them very easy to implement in the multi-party setting. And at the end of this distributed post-processing, privacy amplification is applied, also redundantly and share-wise, to remove not only the information that it learns from the quantum channels, but also the key material that comes from the potentially corrupted QKD pairs. So now, our experiment is just a particular example of the protocol I just described, where we implement a 1.25 gigahertz polarization encoding MDI-QKD system with a silicon photonic modulation chip. And we only provide Alice with redundant devices. Specifically, we protect her against one corrupted device of each kind, exactly. So one CP unit and one QKD module. And in this slide, you can see a schematic of the setup, the secret key length we extract, and some experimental parameters. And more details can be found in the long video presentation on YouTube. And that's it. Thanks a lot for your attention.
Thank you very much, Victor. I pass to Sean for the Q&A session.
Okay, and then we thank all the speakers, but unfortunately, there is no any question. Okay, there is one question from Lavey.
Okay,
there is a question, buddy. Yeah, and then I will let you to ask question. This is a question.
Okay,
for
thank
Victor.
you.
Yeah.
Question for Victor.
Oh yeah, it's a beside to use. Okay. It's a question from Lavey, Emilian, Claude to Victor. It's a bit sad to use many devices and to kind of waste their performance just to ensure that at least one pair is working properly. Would it be possible to have an assumption on the maximum number of corrupted modules to extract more key rate from the combined use of non-corrupted devices? For example, if 3 QKD devices are used but only one is corrupted, it would be nice to effectively use the key of the second non-corrupted devices. Victor, please. You can also see the question in the Q&A.
Okay, I'm not sure if I understand. Is he asking if the keys obtained by the corrupted devices can be also used for the final key, like not removing them with privacy amplification? If it takes too long, maybe we can talk in the meet and greet room, because I don't think I understood properly the question.
Yeah, I think he just suppose you have some assumption that suppose only one is corrupted, it will be effectively for your protocol. Can you read the question in the Q&A?
Yeah, if that is the way I can read it. Okay.
Yeah, you can read it.
So, so the assumption is that you need one honest QKD module at least. Okay, that is what you need. And if you have that, then you of course can extract a key, but that is the worst case scenario. If it is up to the users to decide their assumptions. So maybe they can decide that more than one pair of QKD modules are honest, and in that case, they will be capable of extracting a longer key, but that is up to the users. There's like some sort of security policy, and they make the choice of, okay, at most we have 2 or 3 corrupted pairs. But of course, to save resources, what you will do is something like, and this is how we thought about this, you will do something like, okay, if I want to have one secure pair, one trusted pair, at most I'm going to need, let's say, 5. Like, I am sure that 1 out of 5 will be safe. Or maybe someone else is like, if I have 2, probably one of them is safe. It's up to them, okay? Like the minimum amount of devices to obtain 1 key. That's how we thought about this.
Okay, thank you, Victor. And then Vadim, please ask your question.
Oh, I also had a question to Victor. So if we wanted to implement this protocol on standard QKD hardware, would you only need to modify the software? Would you need to make changes to the hardware? So imagine we have a commercial network installed and the user has like 2 QKD devices, 2 different vendors. Can the existing today's QKD network actually run this protocol with minor modifications?
Yeah, essentially you only need software modifications, okay? Because actually this experiment, and in the longer talk, there are more details about the experiment. The experiment was done by Feihu Tu and Wei Li, and they use kind of the same setup, like something they already had from previous experiments, as far as I know. So you don't need new hardware, okay? This QKD pairs, like they implement independent QKD protocols, QKD sessions, like independent ones. And then the post-processing, what you need is essentially, because the more resources are basically involved in the post-processing, but the post-processing can be done by computers, like laptops. In our experiment, they were standard computers. So you don't need new like quantum hardware to implement this redundant devices idea. You don't need that.
Okay, and then I noticed there is one comment from Erica Anderson. I think it's just comment to the previous question. If I understood correctly, at the most 1/3 of devices can be corrupted. That's the assumption. That's yeah.
Okay. There exists 2 different kind of devices. So we make a difference between the devices that implement the quantum communication, which are the ones we call QKD pairs, and then the ones that implement the post-processing. Okay, so we distinguish, like the users can decide how many QKD modules, the ones that implement the quantum communication, are corrupted, and how many CP units, like the computers that implement the post-processing, are corrupted, okay? The first kind, the ones that implement the quantum communication, you need one of them to be honest to be capable of obtaining a key, a positive key. But the second kind, which are the CP units, since you need redundancy and you need things to be post-processed by a majority of honest units, you need that at most, actually less than 1/3 of them, of your computers, are corrupted, okay? So the simplest case is you have 4 computers, you can tolerate 1 corrupted one in the post-processing, for instance.
Okay, another question for you. It's also from Erica Anderson. It's in commercial QKD setups, the post-processing is likely hardwired and cannot be modified.
I don't know how to answer that. So in commercial QKD setups, hardwired, what does that mean?
I think it's probably using the FPGA program that you just you first have the logic and then you input in the FPGA. Something like that, yeah.
Yeah, so in our proposal, you need some extra classical channels that communicate some of your computers to the others and so on. Of course, it's more hardwired than standard QKD. That is something that you can't avoid. Of course, because we assume that Eve is very powerful and she fully controls all the corrupted devices. If you, for instance, assume that they don't collaborate with each other, like this computer is compromised by this vendor and this one is compromised by this other adversary, then you can reduce the number of computers, and so the setup is less hardwired, probably, I would expect.
Okay. I have a question for the Ernest. What kind of, for your theory, I think it's a good one, but what kind of attacking strategy are you using? I mean, is it a general coherent attack or just collective attack?
Right. Okay. So what we have currently written up is in the collective attacks analysis, although in principle, there is no obstruction to extending it to coherent attacks using the entropy accumulation theorem. But we are just doing that together with the finite size analysis. So yeah, it's not written in the work itself that it works against coherent attacks, but it's not too difficult to extend it to coherent attacks. Yes.
What do you expect the efficiency will change if you're using the
you mean whether the security analysis will be worse for the coherent attack case, you mean?
No, I mean the efficiency, because I think you probably need higher efficiency a higher heralding efficiency to get to secure against the coherent attack.
Well, in the asymptotic sense, it doesn't change things because for that it's possible to do a proof using entropy accumulation where the asymptotic rate for coherent attacks is the same as collective attacks. But for the finite size analysis, yes, there is some difference. There is some care that needs to be taken here, but in one sense, there's only a small difference between the collective and coherent attack situation, but it's possible to modify the protocol for collective attack situation in such a way that the finite size effect is smaller. But that really requires one to trust the collective attacks assumption. So mainly the difference is in finite size analysis, I would say, as an overall summary.
Okay, thank you. Any further question from the audience?
If there are no more questions, I propose that we move to this, how called, break room and see you there. You can ask meet and greet room. So please move there and you can ask your questions directly to the speakers. And in the session room, we meet in 20 minutes for a tutorial by Eleni Diamanti. So thank you all the speakers and see you in 20 minutes. Or in the break.
Okay, maybe I think we can actually start. So good morning or good evening, depending on the time zone. So I'm very happy today to welcome Eleni Diamanti to present a tutorial about practical aspects of quantum key distribution and beyond. This tutorial is now set for roughly 1 hour, and then we have 50 hours for additional questions. But I talked to Eleni, and Eleni as well will encourage you to ask questions as well during the tutorial itself. And that is something then that I will feed in and voice as I see those questions. And that actually helps as well to make a tutorial a little bit more interactive. So don't shy away to ask questions. And then we can go for this. And I think basically with this one, Eleni, without further ado, please go ahead with the tutorial. Thank you.
Thank you very much. Thank you very much, Norbert. Hello, everyone. Good morning, good evening, good afternoon, wherever you are in the world. I would like to thank you all very much, and especially the organizers for this year's QCrypt, to have invited me to give this kickstart this series of tutorials for QCrypt 2020, which is a very special one, of course. I think they have done a fantastic job in making this a virtual event. So I would have very, very much liked to interact with you all in Amsterdam today, but we'll do the best we can, and I think it's the conditions are good online. So I'm going to talk today about various aspects of, in particular practical ones, of quantum key distribution and applications beyond QKD. So I should say that this tutorial, in the great tradition of the QCrypt tutorials, is not directed to QKD experts. Okay, it's actually directed to almost everyone else except for QKD experts. So, so I've basically tried to cover a few aspects and try to answer some questions that I think I would ask if I was not in the field, but around the field. So if I was working as a theorist or an experimentalist, physics, computer science in the field of quantum communication and cryptography, but not specifically in QKD. And because we've seen this now, this field evolving for many, many years, for some decades. So I think a legitimate question would be, what are you guys doing right now? What are the challenges? How come QKD exists for such a long time, but there's still so many protocols and so many different implementations, and how come it hasn't been also widely adopted in the market yet? So what I'm going to try to do is to convey some of the challenges in this field and tell you how complex it is for people working in this field to actually solve all the equations and challenges that come together to make a system work and actually be useful for specific applications. So let us set the stage first, very briefly, before going into the outline. What are quantum communications networks? We are going to be talking about quantum communication networks. So of course, a quantum communication network is a kind of a little bit different in the sense of from a normal network or a normal internet, if you want, in the sense that now we're talking about physical devices. And as you know, of course, in quantum communication, we're encoding the properties of quantum information in quantum states of light. Okay, we're coding the information in properties of quantum states of light. So we're using photonic resources, quantum photonic resources, and we of course need a channel, a medium to propagate this light, this quanta of light in optical fiber or free space channels, and to perform this ultimate goal of quantum communication, which is to transfer quantum information between distant parties. So now these distant parties can of course be client servers, they can be memories, they are network nodes that can have all sorts of different functionalities that can vary from a simple photonic client that just detects, for example, single photons or just sends single states, quantum states, or go up to a few qubit processor or even a quantum simulator, and even at a later stage to a universal quantum computer. Okay, so there is various degrees of complexity in the nodes. And of course, what is interesting in the network is that we can have untrusted users, devices, and nodes. So this is going to be the focus of this talk. And we're also worried about efficiency in the sense that we need to use optimally our communication resources. So the general goal of what we want to do is to analyze and implement using the techniques that we have from quantum photonics to demonstrate a provable quantum advantage in security and efficiency for communication and distributed computing tasks. So this is the general idea, let's say, in this field. So now quantum communication networks come in different flavors. So there was this roadmap that was published a couple of years ago by Stephanie Wenner and colleagues that shows this nicely, that a quantum network can be understood as we said, with links and nodes that have, as we just said, different degrees of complexity. And depending on this complexity, you can achieve certain functionalities, okay? So here we're going to focus mostly in these lower stages of the quantum network, it can also be understood not only as a functionality, but also as a timeline, okay? So the upper you go in the stages, the tougher it gets, so it will take us longer to get there, but we also, it gives us access to more and more complex functionalities. So here we're going to focus mostly in the lower stages of the network, the ones that have trusted node, prepare and measure. I'm going to talk about this a little bit, or that are based on entanglement generation. And you will, as you see in the column on the right, these essentially give access to essentially quantum key distribution, which is the main protocol we'll be talking about, but also to some other protocols that we'll be discussing towards the end of the talk. So you see why quantum key distribution is so present. It's the protocol that we have managed to know how to do well in our practical systems, and this is why even nowadays half of QCrypt or more basically is focused on QKD, because it's one of the most important functionalities, extremely useful as well, and it works as a pilot functionality to understand how difficult, how much more challenging things become when you go from the textbook explanation of a protocol to an actual implementation.
The one question is actually, because you mentioned it, what would be a free space channel? You mentioned that briefly.
Free space channel could be understood as a satellite, of course, as a satellite to ground channel, or it can be also linking two locations on Earth via the atmosphere and not via optical fibers. Okay, so it can be understood as anything that does not go through an optical fiber, and it includes, in my definition, sorry, it should have been even more clear. In my definition, it also includes satellite links. So we're going to first go through some reminders on QKD. Then I'm going to define a bit briefly criteria and measures of performance of QKD systems. I will give some selected examples of configurations and current challenges. So this is going to take the biggest bulk of this talk. And then I'm going to mention some applications beyond QKD. And I'm going to conclude with the importance of having test beds and some concrete use cases that will be tested in those, that can be tested in those tests. So some reminders on QKD. So what do we want to do with QKD? We want to secure our quantum communication network link. So this is, I was just saying, is the landmark application of quantum application. It has driven the field for many, many, many years now. I guess I cannot start this talk by not giving, as I was saying, the textbook explanation for those of you who may, but I think everybody in the audience must have known what is on this slide, but may be limited actually to what is on these slides. And this is the goal here, to go beyond what is written here. So we know we have Alice and Bob. This is a point-to-point link that I'm showing here. It can be Alice can be the transmitter and Bob the receiver, but you can also have an entangled photon source in the middle that is sending the photons to both Alice and Bob. The idea here is that they are linked by a quantum channel and a classical authenticated channel. And the very, very basic idea of quantum key distribution is, thanks to the principles of quantum physics, any information that the eavesdropper, that we call Eve, might try to retrieve from attacking, let's say, the quantum channel or listening to the classical channel of communication between Alice and Bob, will necessarily lead to errors in what Alice and Bob will get and will obtain as information, and therefore they can actually extract the secret key by analyzing this data and including the errors that they get. So it is possible to detect eavesdropping on the communication link. Okay, so this is basically the important property of quantum key distribution, and this means the main property again of QKD is that there is no need to make assumptions on the computational power of the eavesdropper, which is known as information theoretic security. So this represents a huge change of paradigm with respect to classical algorithms that can offer computational security. So I'm repeating again the text with definition, which basically means that if a new high-power computational techniques become available in the future, including by a quantum computer, for example, or other unknown increase of the computing power, it will be possible to render obsolete and vulnerable some of the cryptographic techniques that are used nowadays. So QKD can offer this information theoretic security. So of course, this is not the whole picture. So it actually takes a little bit of time after you get into the field of QKD, even first, let's say, year PhD students that are working in this field, or even some lots of physicists, especially, that work in this field, but not on QKD, on more quantum communication, they believe that this is enough. That's what QKD does. So it offers information theoretic security, it's unconditionally secure, and it solves the problem of secure message exchange, and it secures network links. So this is the end of the story. So of course, once you go into more details in what actually QKD does, this is not the end of the story. Okay, QKD does not offer standalone cryptographic solution. It has to be combined, and this is where you understand that it's a probably key distribution. It's not probably the right word. It can be called key agreement. There are many ways of calling it. It's the key establishment, exchange, amplification, negotiation. There are all sorts of different ways that people prefer calling it rather than key distribution. Needs to be combined with authentication and message encryption algorithms. Okay, so you see here, in order to actually perform in practice the cryptographic functionality of secure message exchange, this key agreement QKD does only part of the job, and it has to be combined, as I just said, with solutions for authentication and message encryption. So there is all sorts of different combinations. I have some examples here of how this can be done. So you see here that the key agreement, the key distribution, is one of the main blocks that are needed for such a functionality. But it has to, for a full information theoretic solution, that would be the ideal. You need to combine it with, for example, one-time pad that is relatively slow. So there is all sorts of different, let's say, trade-offs that need to be taken into account when one designed your cryptographic functionality that includes quantum key distribution. And the fact that this is correct and that QKD is only part of the full cryptographic functionality is one of the reasons why it has been criticized as not enough, not sufficient, let's say, for offering full security against attacks by quantum computers. So there is no ubiquitous solution. There are trade-offs between security risks and ease of implementation. This wholly depends on the use case. But what is correct and should be said is that QKD offers information theoretic long-term security of sensitive data. This is understood and accepted globally, and is robust against the powerful store now, decrypt later attacks, which are the type of attacks that you need for a big let's say, amount of data that transfer over in our communication, worldwide communications today. So QKD has to be understood, and this is going to be the end of this more protocol, more functionality, let's say, introduction to QKD, has to be understood as offering an extra security layer, an extremely important security layer to the other functionalities that can help mitigate the risks that come with future improvement progress in computing. So once this has been understood, and we all agree on the role of QKD in the cryptographic and the cybersecurity landscape, one has to go to the practical world, okay, and see how can you do quantum key distribution in practice, okay? Once you have positioned it as a cryptographic functionality, you want to see how easy it is to do. And this is the other, let's say, axis where one can say that it changes tremendously with respect to the current cryptographic practices, because obviously it relies, QKD happens on the physical layer. It has to do with photons, with fibers, with physical, let's say, communication links, and this is something that is not common in cryptographic scenarios. So what happens in QKD in practice? So a few years ago, 4 years ago, we published this review with some of our colleagues on state-of-the-art of point-to-point fiber optic QKD That was in 2016. As you see here, this graph, it was a secret key generation rate as a function of channel loss or fiber distance. So that was in optical fiber with telecom wavelength. That was a figure that took us a long time to do because it's not easy, right? You need to compare sometimes protocols that are not at the same level of maturity, that you have to make some assumptions. The security proofs, for example, may not be at exactly the same level, and this is extremely important. And this is why we had split it back then in mature protocols and emerging protocols. I'm going to, in the configuration that I'm going to choose later on to highlight some of the challenges in the field, you will see that the measurement device independent system, the MDI, has jumped up to the mature protocol since 2016 because it has been it has progressed a lot. But there are some important information that you can already understand from this figure. First of all, that there is the two main figures here is the rate and the loss, okay, the fiber distance. And also you will notice that we had highlighted as well practical systems like the single photon detectors that were used for the implementation, where you see that cryogenic detectors were particularly helpful for extending the distance in those systems, which, by the way, has been extended even more since then. And I'm going to show you a few examples afterwards. So what we also can see, this is, as I repeat again, I emphasize, it's an extremely rich field with constant innovation in both theoretical protocols and practical implementation. So the question is, how do you navigate in this rich offer in the field? You see all these protocols and those implementations. For the non-expert, it's not always easy to understand why there are so many protocols, what do each of these protocols offer, what are the challenges that they respond to, in a sense, and how are these useful for specific, as I was saying before, use cases. Okay, so this is something that I'm going to focus on now. We're going to go through the measures of performance and the criteria of this. So let's start. The very first thing that you saw here is the distance, okay, and this corresponds to one of the main differences with classical cryptographic systems, that they do not care about length, right? About the distance between the parties where the secure message exchange has to occur. This was a criterion that doesn't enter into the picture. And so this is a big difference with respect to when it comes to quantum key distribution. So of course, it's due to the fact that we have an inherent limitation due to the optical fiber loss. So point-to-point links, as you just saw in the previous figure, is limited. And therefore we have to somehow mitigate this factor. Okay? We have to find a solution. So what are the solutions to this? Is to go to networks, QKD networks, and to also include satellite links into the communication. These are not antithetic things. So a QKD network can also include a satellite link. Okay, so but I'm treating them separately here so that I can focus a little bit more into specific points in each one of these solutions. So we're going to go through a little bit in the details later, but what is important here is what I want you to understand. When we're talking about a QKD network, what matters? We want to choose the topology, when we want to choose what protocol and what system we're going to use. What are let's say the designer or the end user, what does he or she need to look at? So the very first question that comes into the picture is, can I accept trusted nodes in my network? Okay, and this is equivalent to say, can I accept prepare and measure schemes? I hope it is clear to everyone in the audience why these are linked, but I may repeat this again, is that prepare and measure schemes means that Alice sends quantum states to Bob, who measures them, and they perform the QKD protocol. And therefore, if you want to extend the distance in using such a prepare and measure scheme, you have to do something like the thing that is shown in the figure here with satellites, where you see a satellite that is creating a key using a point-to-point system, let's say, with a ground station, and then they would like the satellites, via the satellite, they need to perform secure message exchange with a very distant location. So what do? Is that the satellite takes the key, so has the key and creates another key with a ground station in the other location, performs the XOR, and this is how they send the secret message in the second location. What does this mean? That the satellite in this picture is a trusted node, okay? And basically this is the main property of such pre-prior measure schemes, that in order to extend the distance, you have to trust the intermediate nodes. So for some use case applications, so from some use cases, this is perfectly acceptable. For some others, it is not. So in that case, you need to use other schemes, as you are going to see. So see, this is a second question. Do I need some untrusted nodes at least? And then do I even need to go towards device independence? So device independence, we saw a whole session earlier this morning about device independence protocols. It's one of the most important aspects in quantum information, especially quantum cryptography these days. It means, of course, that you do not have to worry in a QKD point. From a QKD perspective, it means that you don't have to worry about imperfections in your devices, and you have to have a minimal set of assumptions on your system. So it's extremely nice, obviously, a very desirable feature. But of course, as we're going to see a little bit later, it's extremely hard to achieve, and it needs violation of Bell inequalities, etc. So these are the questions that we want to have. Do we need device independence? And then another question that comes more and more often into the trade-offs of the criteria: is it possible to ensure upgradability towards long-term quantum networks? Remember when I showed you the stages of the quantum networks? The idea here is that when you are right now in the layer, when you deploy your QKD network nowadays, you need to think that in a few years you will have quantum memories, you will have more advanced quantum repeaters. So how upgradable is the current network that you are deploying to such stages, let's say, of the quantum network? Can it accommodate for quantum computing devices when they will be available, etc.? And of course, another issue with this is to define appropriate network interfaces. This is a big question that we're not going to treat a lot in this talk, but it's also obviously very relevant for anything that you will want to do. From satellite now communications, the second, let's say, avenue to going to long distance link. There are many questions and criteria that one wants to answer as well. What is the satellite orbit and payload? How do you want to design it? There are low Earth orbit, medium Earth orbit, geostationary Earth orbit satellites. They differ vastly in terms of coverage, loss budget, and requirements for the pointing and tracking system. And therefore, not everything is possible and not everything is doable for specific use cases. One has to also put into the balance of the choices that you have to make in practice if you also want to use satellite constellations or nanosatellite technologies in specific cases, instead to cover, for example, to increase your geographic coverage in lower orbits, instead of deploying, for example, geostationary satellites that are very, very far. They have a good geographic coverage, but they have very constrained loss budget. So you see the trade-offs that come into the picture. Then the second important property after the distance that we analyzed here was, of course, the rate. At what rate can the secret be generated? So this is important as well for some use cases. And it's also an important difference with classical systems, okay? So contrary, again, to classical cases where we can now extend the rates to very high values, here we have theoretical bounds for repeaterless links for QKD that show that it is not possible to extract infinite, let's say, more than specific bounds of secret key over noisy quantum channels. So how do you do to avoid this, to increase your rate? You either invent new protocols or you apply multiplexing techniques. So let's go through the important criteria here. When you have new protocols, the first thing that you need to worry about is, of course, the status. What is the security status of your protocol? Can you provide a security proof that is at the same time composable and includes finite size effects? So for the non-experts here, composability is the property of security proofs that ensures that you can use it in a more general scenario where several protocols are performed one after the other. together, so you can kind of put together the security parameters. And finite size effects, it means that you calculate your key rate considering that you can only have a finite amount of size of data and not asymptotic, so you don't calculate asymptotic rates. You have finite amount of data and you have to take this into account. It's an extremely important factor when you perform your parameter estimation and you do your classical processing. So in terms of security, what also matters in terms of practical security is identifying the side channels and of course countermeasures and the complexity of classical post-processing. And finally, in terms of multiplexing, this brings about the question of cost effectiveness of the systems, that one has to build. So one important aspect there is the compatibility with the telecom network infrastructure. Why is this important? Well, because it takes a lot of money. It's very expensive to deploy an infrastructure. So being able to use it in a mutualized way between quantum and classical technologies is obviously extremely important, whether you're going to use dark fibers as well or fibers that are also used for classical communication is extremely important. And finally, the question of employing photonic integration circuit solutions that are also advancing very rapidly as well, independently of the quantum field. Improves the maturity of your systems and the compactness and decreases the cost. And finally, from a market adoption point of view, the maturity and availability of components is extremely important. So basically, what I have tried to do here is in 2 slides, I have tried to summarize. I was very proud of this. I have tried to summarize all the keywords, let's say, here they are. One here, all the keywords that come into the picture when one needs to use QKD in practice, okay? When you really want to do something with a text-to-bit protocol that you all know. So remember all the keywords in blue and red here. Every single thing among what you just saw matters, okay? And there is no ubiquitous solution. I hope this is not controversial. I hope everybody among the QKD experts agrees that there is no system currently that can offer a good solution to every single one of these criteria that can be universally used for anything where you want to have long-term and information theoretic security for your data and for any use case. So what I'm trying to convey here is that all these criteria matter and they are covered in bigger or lesser extent by the various systems that are currently being developed. And this is what answers to the question that you may be asking when you're not in the field. How come we haven't picked one protocol and one system, use it for everything and make it available everywhere and use it for all our use cases? Because there is many factors that come into the picture. So what I've tried to do now is I'll try to give some examples of experimental systems and what are the challenges, to what questions have the systems answered and what are the current challenges that they are still facing to make them the ubiquitous solution, let's say, of QKD. This is obviously my own selection. This is by no means covers the whole field. For example, I have put aside for the moment technologies like high dimensional QKD that is also increasing in importance, or more, let's say, technologies that are progressing now. So this is by no means covering the whole field, okay? They just cover some aspects of that I find important. So obviously, I'm going to start with the BB84 protocol with decoy states. So if I put it in the matrix, let's say, of criteria and performance measures that I just gave before, this will be a protocol that is prepared and measured. It uses weak coherent pulses for its implementation, so that it's a qubit-based protocol where the single qubit, single photons are simulated by weak coherent pulses in experiments, and it needs detection with single photon detectors. So one, I would say, property and very positive characteristic of this technology is that it has provided up to now very high TRL, as we say, technology readiness level, systems with record-breaking implementations. So I'm going to show a few examples of this record-breaking implementation to show you also the diversity of systems that people have used to answer to all the challenges that we just saw before, okay, in terms of rate, distance, compactness, integration, and these type of things. So, for example, this is a very high rate system from Toshiba, where you see that they have achieved a 10 megabit per second secret key rate. So this system has used phase encoding, okay, for the Baby 84 system, and you also see here that there is a multiplexing. There is a multiplexing for the data synchronization symbols, a signal, using wavelength division multiplexing techniques. So this is from a secret key rate point of view. This has given a very high result, obviously over a moderate distance, as you saw in the review graph that we saw earlier. There is always a kind of trade-off between distance and rate. Sorry. So from a distance point of view, this is an experiment by Geneva, where again some version of the BB84 with decoy states, where this is now the encoding is done with time beams. A very simple implementation that with ultra low loss fibers that used also superconducting nanowire detectors, and they managed with the system to go to more than 400 kilometers in this optical fiber using these cryogenic detectors at very low rate, of course, but it's possible, let's say, to break again this record in the distance in optical fiber. And of course, if you go to satellite link, this was the protocol that was used in the first demonstration of QKD with the misuse satellite in China, over from satellite to ground link over 1,200 kilometers. This was the protocol. It was not done at telecom wavelength. That was done near infrared wavelength, and the protocol is operating. And the system is operating at not operating at daytime, but this showed that it is technologically possible to perform this type of protocols over this type of very long distance. From a photonic integration point of view, I'm highlighting here some results from Bristol, with where we see silicon integrated transmitter photonic integrated circuits for performing BB84 in timing, polarization, and also the coherent one-way protocol. And so the difficulty here when it comes to BB84 is obviously it comes from the single photon detectors that are harder for the moment to integrate on a chip. So you see that several of the challenges that we discussed earlier, remember the blue and red highlighted points that we saw before. From a security point of view, this is kind of okay. We have the post-processing is okay, and so the technical challenges here were mostly linked to the rate and the distance and the photonic integration, and these are the latest results that you see. For this protocol. So it's an extremely promising protocol. There are some remaining challenges, of course. The important point is that it uses trusted nodes. As we said earlier, it's a prepare and measure protocol. So this cannot, in a sense, it's not designed to be upgradable in the sense that we discussed earlier. So it's not based on entanglement, and it's not, let's say, immediately compatible. Of course, you can imagine links where it is possible to aggregate technologies, but it's not immediately designed to be combined with quantum memory. Another characteristic, it has another challenge, let's say, it still has some vulnerabilities linked to the detector side channels and uses single photon detectors. I'm going to put this as let's say, as a minor drawback, despite the advances in single photon detectors these days. It is correct to say that cryogenic detectors provide a non-negligible performance enhancement in some systems, and therefore such systems that are typically heavy and not easy to operate are needed for good performance. So the second configuration that I wanted to highlight is continuous variable QKD. So this is a protocol that we're working on in my group as well. So I'm going to highlight a couple of aspects that are linked to its practical implementation. So this is also a prepare and measure scheme. Instead of encoding information on properties of single qubits, It actually encodes information in quadratures of the electromagnetic field, in particular of coherent states. So it also uses the same, let's say, photonic carriers as BB84, but encoding the information elsewhere, let's say in the field, not in the properties like polarization, time, bin, or phase, but in the amplitude and phase of the coherent states. And because of this, the information can be detected with coherent detectors that can be homodyne or heterodyne detectors. So the advantages, let's say, of this technology, it has high compatibility with telecom networks. I'm going to analyze this a little bit further in a second. Also, it can be easy to multiplex with classical signals, and it can offer high level of photonic integration, especially because it is also possible to integrate better the photonic the detector technology. So because of its potential, it has also, this is a technology that is being developed in Europe within this Quantum Technologies Flagship Consortium project that is called CIVI. So let me highlight a few things on these protocols. Here you see, here for the non-experts, sorry for the technical details for the non-experts here, you see an experimental system that basically shows one characteristic that when you read the protocol of continuous variable QKD as a theorist, you are not going to see immediately, is that it needs a local oscillator. What does this mean? To perform this coherent detection, you basically need to have an external phase reference, a signal that is called local oscillator that has to interfere with the proper signal on a beam splitter, and then you take the output of the two photodiodes here, you subtract the signal, and this is what gives you the measurement of the quadrature of the signal, which is, let's say, amplified by the amplitude of the local oscillator, and this is why this is important. So the fact that you need this local oscillator to perform your system adds an extra complexity in the experimental system, because it means that you have to somehow transmit it. You have to somehow either transmit it or generate it in the receiver side. In this particular case that you see here, let's say the historic implementation, it was transmitted over the same signal, and which opens up potential side channels as we are going to discuss. It's also the system, let's say again, the historic system that was used for long distance operation in the last years. Also used pulsed operation, used this homodyne detection, and relied on Gaussian modulation. Maybe you saw, if some of you saw the talk by Anthony Leverrier yesterday, you would have seen that this is an important characteristic of this protocol, that you have to modulate, let's say traditionally we have modulated with Gaussian distribution the signal to improve the rate. So now, if you want to leverage the compatibility of the system with telecom networks, what you want to do is you want to evolve the system even more. So you want to go towards bandwidth efficiency QKD. So this is an example of how all the challenges that you need to solve if you want to make your system even better. Okay, if you want to even make it even more better integrated into telecom networks, more efficient, more faster, going in longer distances, etc. So you have to take care of each one of these. And for example, in this particular case, you don't want to transmit anymore the local oscillator. You want to generate it locally for many reasons. You don't need any more multiplexing. You don't have any more the intensity limitation because of the local oscillator and no related side channels, but it opens up more constraints, new constraints in laser bandwidth and in recovering the phase information. You also want normally to use optimally the spectrum to avoid intersimple interference and use pilots, but this also opens up new challenges with using digital signal processing and also potential security concerns, because you have to take care of possible leakage of information by using these pulse shaping techniques. Instead of homemade homodyne detectors, you would want to use these commercially available integrated coherent receivers, but which have to have very high bandwidth and low noise. So this is also not easy to do. And you would also need to perform, for a better and more efficient post-processing, you would want to perform discrete modulation, like you saw yesterday and in the talk of Anthony. And so this helps as well to to go towards most efficient, more efficient and systems. So you see here, what I want to highlight here beyond the technical details is that you need to bring together in order to be able to leverage, as I was saying, this capacity of the system to have a better link with a better integration in telecom networks. You have to bring together big expertise from all various domains, especially from engineering, but also from security proofs, to be able to work to maximize, let's say, the performance of such a system. From a photonic integration point of view, I'm going to go a little bit faster here. You see the silicon photon integrated circuits that are done by Singapore. On the left, it's results from our group on short noise limited homotime detector. So you see, as I was saying before, that here you can actually integrate. So it has high. Yes, Norbert, you want to? There is a question. I cannot hear you.
Okay, now you can hear me. Good.
Yes.
There's one question actually in that asks about the local oscillator option, the true local oscillator, or the other one. Basically, what do you think is most suitable for free space CV-QKD?
Oh,
because
so
we talk mostly about fiber, but what about CV-QKD?
So I think if we're trying to look at, for example, satellite link, this was actually my very next thing here, the one that I was going to talk about for the feasibility study of satellite link. I don't think it's even possible, personally, my opinion is that it's not even possible to do it with a transmitted local oscillator. And I think one has definitely to go with a local oscillator, so generated in the receiver, because at this type of very long, let's say, already, as again, I was going to say the weak loss resilience of CV-QKD systems, it means that already there is, it's quite difficult to get over losses in the system. For many reasons, it's higher, the resilience to losses is lower. And so by adding this extra difficulty of sending the local oscillator in high loss channels, it means it makes it very hard to perform the coherent detection. So for me, it is clear that the local oscillator solution should be the one that is accepted in both fiber optic actually and free space. So it would be my answer. So yeah, I was going down with photonic integration. So I was like highlighting that it's, as I was saying earlier, that it can offer this technology higher degree of photonic integration. In terms of satellite link, it's less obvious than with BP84 with the co-state that it's possible. We have several groups who have performed feasibility studies. These are the results that we have performed in our group with specific, of course, assumptions where we assume high state-of-the-art pointing techniques, high repetition rate that is not yet available, local oscillator, exactly, which was the question, and specific, let's say, moderated atmospheric effects. We have also applied, performed the security analysis, security analysis for fluctuating channels. And the idea is that you see that in practice, under these assumptions, in principle, it would be possible to perform this protocol as well over a LEO satellite link with in our simulation, the ICE is on board the satellite and Bob is on the ground. So it's a satellite to ground link by carefully binning, by carefully grouping the data under specific transmittivity channels, and to be able, let's say, to group the transmission physics for which it is possible to generate a secret. But this has not been experimentally performed yet for this protocol over satellite link. So the challenges that are remaining for this configuration, again, this is a prepare and measure system, so it requires trusted nodes. The loss resilience is weaker than with other protocols, and it also requires complex post-processing. Let me go through the other two configurations that are going to be a little bit faster because they have been covered very nicely, especially the measurement device independent twin field QKD. I was very much inspired by Marco Camarini's tutorial from 2018, QCrypt, which was very complete and very nice. I definitely recommend to you, if you're interested in this technology, to go and take a look. But if we put it in the same framework as the discussion that we've had up till now, so this is a prepare and joint measure protocol, okay? So what does this mean? It means that, let me show you these two pictures from measurement device independence on the left and twin field QKDs on the right. These systems basically rely on the first one on 2-photon interference and the second one on single photon interference on an intermediate relay. And so the idea behind the measurement device independent twin field QKD is that via this interference technique, you avoid essentially all the detector side channels. You put them in the intermediate. You put all the detectors in the intermediate relay that can be untrusted, and therefore this improves, in a sense, the number. It introduces a few trusted nodes, so it improves, in a sense, this upgradability that I was talking to you about earlier, among the important criteria that for QKD networks. Additionally, the twin field system that relies on single photon interference offers beats the repeaterless bound, and so it offers the prospect of higher rates, and they both offer higher loss resilience. You can see it here as well. Again, this is from Marco's tutorial on the twin field QKD. It offers higher rates than it's possible to achieve with other technologies, with repeaterless technologies, and they both offer high loss resilience. You are going to hear, you have already heard quite a bit about measurement device independent in this conference, and there is going to be as well a talk about the latest twin field experiment that has exceeded 500 kilometers. So these offer high loss resilience and potentially high rates, but there is no obviously perfect, as I was telling you, there is no perfect systems. So they both require rather complex implementations, especially for free space. So currently it is considered quite hard to perform such a protocol over a free space and even more over a satellite link. And again, you get a performance enhancement with cryogenic detectors. So there is this use of single photon detectors. Finally, last protocol that I wanted to highlight is, of course, entanglement-based QKD that is almost as old as BB84. So this relies on entangled states. It uses single photon detectors, and it has the advantage of requiring less trusted nodes. It is also like, oh yeah, I forgot to mention this here, the compatibility with star topology of networks, which basically means that you manage to link all of your nodes in a way by using the least possible number of optical links. Okay, so this could be interesting for topology for reducing, let's say, the necessary resources in QKD networks. So this is an advantage of this type of protocols with basically relay nodes, either with entanglement source or with this relay that are used in measurement device independent and twin field topologies. So these protocols also offer a path to device independence, and they have high loss resilience. One thing that I really want to highlight here, and there is this, I have noticed that there is a common misunderstanding potentially with non-experts in the field, that somehow they think that entanglement is equal to device independence, that from the minute that you have done an entanglement-based QKD protocol, you have achieved a device independent implementation, and this is incorrect. It's actually a lot harder than just emitting entangled states to perform device independence. It's harder because you need to rely on specific Bell inequalities. You have to have loophole-free Bell test, very stringent requirements on your detector efficiency and on your losses and your timing. And this is something that is out of experimental reach right now. I want to highlight here two results. The one is from Vienna and Bristol, a full connected graph that was done using entangled photons, and of course the latest result from the misuse satellite, where it was shown that with the entangled photon source that was on board of the misuse, it was possible to perform the entanglement-based QKD, the BBM92 protocol, between two ground stations that were separated by 1,120 kilometers in China. So here, of course, the difficulty that you can see is that the way that this is done, the ground station needs to be in sight view of the satellite for this to work. but you see that it's experimentally feasible. So what are the challenges when it comes to entanglement-based QKD, which is, as I said before, also, let's say, more naturally upgradable and provides a path to device independence, is that you need more complex technology like entangled photon sources. Although this is a mature technology nowadays, it still remains a technology that is not fully available, easily, let's say, available in commercial market. It requires single photon detectors. Once more, cryogenic detectors provide performance enhancement. It is also, when it's not device independent, which is always the case up to now, it's also open to detector side channels. And again, device independence is challenging. It's not immediately within experimental reach currently. So this concludes the main, let's say, body of material that I wanted to cover. I hope what I wanted to convey again is that the measures of performance that are interesting for QKD networks, and I gave you some configurations that are interesting, promising, and that highlight that there is no system that covers all these criteria, but some of them can offer one or the other advantage as it stands right now. So either very high rate or very high distance or very good compatibility with current telecom technology, or the upgradability towards entanglement-based systems, etc. So this is basically all the criteria that come into the picture when you want to create your to choose your system. So once you know what data you have, what locations you have, where you want, what you want to connect with what, and at what rate, etc., it's possible by knowing what is available, let's say among these experimental systems, to see what is the best choice. So now in the last maybe 10 minutes of the talk, I will focus a little bit on applications beyond QKD and then conclude with a very few comments on test beds and use cases. So what I wanted to highlight here is that key distribution is a very important privity. I hope I have convinced you here why it is important and why we see it so much. But it's still just one functionality that covers a specific protocol in this trusted two-party security model. So as you saw in the figure before, there is other configurations, many more functionalities where it is possible to demonstrate a quantum advantage, even without, in some cases, information theoretic security. So if I want to complete and enhance even more the figure that I showed you before, I can add many more protocols, and even some of them, the ones that are in red, I think I may have missed some, but I think all of them that are in red are covered in one way or another with oral presentations and posters, even at QCrypt this year. Okay, so we're going to hear about entanglement verification, conference key agreement, secure multi-party computing, lots about quantum random number generation, quantum money, mostly theoretical protocols for these ones, but also coin flipping, oblivious transfer. We just saw the experimental implementation this morning of oblivious transfer. We have digital signatures. So you see that the landscape of quantum communication and cryptography is a lot larger than only quantum key distribution. And I think it's not possibly stressed enough how important it is to enlarge these functionalities and gain knowledge from research, from the very advanced research in QKD, to also advance towards these functionalities. So the typical questions that come into the picture when you want to work on these protocols is how do we make them compatible with experiments? For QKD, we have kind of solved this problem, as you saw. We have understood very well what is the security enhancement, how to do it. But for many of the protocols that you see up there in this graph, in this slide, when experimentalists look at these protocols, they're extremely abstract. They require often inaccessible resources or very hard, let's say, and are vulnerable to imperfection. So it has happened, because we have looked in my group with several of these protocols, it has happened that as soon as you introduce loss, for example, the security breaks down. And so you have to obviously adapt your protocol so that it becomes compatible with the experimental reality. And then you see that it's not always easy, but it's possible to perform proof of principle implementations of such protocols, and it's extremely important. Another important question when it comes to these protocols is, when do you claim a quantum advantage? It's extremely important to make a fair comparison with classical resources. The temptation is high sometimes to claim a quantum advantage without having considered properly and to the degree that is necessary all the resources that are available classically if you look carefully enough. Okay, so sometimes we have the tendency to not look carefully enough to see how, let's say that classical techniques are more powerful than we would want to think sometimes. So this is very important. So I'm highlighting here the importance of stressing how important it is to look at this. I'm going to go a little bit faster than planned. I wanted to highlight some examples. You are going to see, as I was showing in the conference, you are going to see lots of talks. Already saw the conference key agreement. You are going to just see after me the invited talk on quantum random number generation by Felix Busquero of ID Quantique. You're going to hear talks about quantum money, coin flipping, and others. So I just wanted to show you an examples that we have considered in the last years in my group, because I know them a little bit better, but maybe I'll go a little bit fast. So one of the protocols that we have considered, for example, was quantum coin flipping, which is the fundamental primitive for distributed computing. And we performed this theoretical analysis that allowed for an honest abort to include imperfections. So this is typically a case where you had to adapt your theoretical protocol to make it feasible, let's say, make it implementable. And this goes in the lower stage here of the quantum networks, because basically the implementation essentially looks a lot like a discrete variable, a BB84 type implementation to perform this strong quantum coin flipping protocol. There as well, it was quite important to compare with the correct classical bound, and you see that it was quite stringent. It was possible to show this quantum advantage in the cheating probability for about 15 kilometers. Okay, so it was harder than a QKD, and this is because these are protocols that where Alice and Bob cannot collaborate because they are one of them is typically dishonest. And we have also proposed an experimentally weak quantum coin flipping protocol, which is harder and it requires entanglement. So not surprisingly, it requires an upper stage of the quantum network. It relies on entanglement because it's harder to perform with, for such a protocol. We have also performed work on quantum money, and we're not going to go through details of this. And then finally, quantum network protocols. This is important. This is the type of protocols that are considered, for example, in the Quantum Internet Alliance flagship project in Europe. So here we consider the multi-party entangled states are one of the main resources in such quantum networks. So what we have done is that we consider proof of principle verification of multi-party entanglement in the presence of dishonest parties. There, the idea is that the very first thing that you want to do when you have access to this type of multi-party entangled state is to verify, for the honest parties, to verify that they have the correct state, that it is close to the ideal state, so they can use it afterwards, if possible, in a composable manner. So this is also something that we looked with other protocols. Okay, for example, we have combined this with anonymous message transmission, where the verification phase also guarantees anonymity. And we have also looked at theoretical framework for composability. So there is lots of work around quantum network protocols, and one of the main protocols that I'm not going to discuss here that are also considered in the framework of this European project, for example, is also delegated computing, that also belongs, let's say, into this category of quantum network protocols. I'm going to conclude with the importance of deploying testbeds and actually performing use cases for going towards the wider adoption of such technologies like QKD, but the other protocols as well. Why? Because by deploying practical testbeds, it is possible to test the interoperability and the maturity of your systems. It's also extremely crucial to look at network integration aspects, which I did not cover today, but these are also very important. It's also possible to do benchmarking for the use cases and standardization, of course, of of these interfaces. The most important examples that I'm highlighting here, of course, in Europe, we had several years ago the so-called QCrypt network, which was a pioneer, let's say, at the time of how it's possible. It was in Vienna area, the deployment of QKD networks, but there have been also deployments in South Africa and Switzerland, Tokyo, and the UK Quantum Communication Hub network, and of course, a very large-scale one in China, which includes several cities, a big number of nodes, and also connection with satellite links, and of course, I highlight here that these are trusted nodes. Now, putting it in the context of the previous criteria that I mentioned in this tutorial, these are all trusted node scenario, right? Like in the way that we have right now, testbed practical deployment of practical testbeds typically does not include entanglement-based or untrusted node, let's say, links. So in Europe, where we have this very large-scale project, OpenQKD, which involves 38 partners from that cover telco operators, QKD developers, suppliers of classical network equipment, academic groups, and end users, which has as a goal to deploy a big number of test beds and corresponding use cases in several parts of Europe. So this is an extremely ambitious project, and I believe it is going to be discussed in more detail tomorrow in the industry session. And so what I want to highlight here is that when you go to such a large-scale deployments, both in China and in Europe, what you see is that it's much more challenging than just putting one QKD system together, right? There is a whole new number of difficulties that one has to face. How many fibers are available? Like, for example, right now, to say our own difficulty with the testbed in Paris is that we need to find out what is connected. We have decided, let's say, our nodes, but we have to connect to see how many fibers are available. Do we need dark? Do we need lead? Do they come in pairs? And what if the attenuation is too high? And what are the correct systems to deploy, depending on all the criteria that we just saw earlier. What is the key management system? What are the encryptors? So there's a big number of questions that need to be answered when you go into such large-scale deployments. In Europe, again, this is my conclusion. This leads towards a quantum communication infrastructure that has been signed by 24 out of the 27 member states of EU. And so the idea is that we're going towards a European quantum communication infrastructure that will include terrestrial and space segments and the open testbeds, and eventually lead to a global quantum communication infrastructure linking with the other testbeds currently under deployment in the rest of the world. We're focusing on improving all the aspects of what we discussed in this talk: the cost, the range, network integration, coexistence with classical signals, further applications for the quantum internet, so the upper stages of the quantum network, and of course, standards and certification. I didn't say much about this here, but this is extremely crucial for anything that goes into market adoption, and a very nice topic as well of global collaboration in the field. And the whole idea is that there is a top-down approach driven by real use cases, where these use cases can cover a very wide range of topics, going from data center storage and interconnection with data backup centers, for example, for finance, to connect between headquarters and disaster recovery centers, critical infrastructure, command and control, high-level governmental communications, medical file transfer, and eventually communication between quantum processors. All of these are use cases, and for all of them, as we discussed earlier, one has to take into account all the criteria and performance that we discussed earlier, and find the right topology and technological solution. So here, with this, I'm going to conclude. I think it is now pretty widely accepted that quantum communication networks will be part of the future quantum safe infrastructure. I wanted to convey the message as well that the quantum communication toolbox is rich, is advanced, increasingly advanced, and becoming more and more advanced, and the QCrypt is a beautiful useful demonstration of how this is the case. I want to emphasize that although the physical implementation of QKD networks is challenging, there are rapid advancements happening right now. I showed you some of them, and they do address effectively all the challenges that you see in this field. So we saw various aspects of how challenging it is and how implementations offer specific solutions to these problems. But I do want also to highlight that we do need quantum technologies, and especially for cryptography, they need to integrate into currently available standard network and cryptographic practices to materialize this global quantum network vision. And it will be possible with this global quantum communication infrastructure to address a range of use cases in many configurations. So with this, I would like to thank you very much for your attention. And say hello from where I am right now, which is a Greek island. And I would have loved to be in Amsterdam, but at least I'm not in the worst place in the world. Thank you very much.
Okay, great. Thank you very much, Eleni. Thanks for this really very nice overview that really touches all of the various aspects about implementation of quantum key distribution. I think as well we would indeed be happy to join you on the island. So we are coming. So we have a couple of questions actually, and the first one is actually a follow-up question by Rupesh. I think that is probably Rupesh Kumar. Rupesh, if you want to ask a question, please go ahead.
Hi, Eleni. Hi, that's a really nice talk.
Thank you, Rupesh.
So I asked the previous question as well. So compared to transmitting local oscillator and local oscillator, the local oscillator based CVQKD system has not been demonstrated more than a few tens of kilometers. So because of the coherence, I mean, line width problem of the lasers. So to improve the transmission distance of LLR, to make it able to transmit from the satellite, I mean, that much of distance, like 40 or 60 dBs of losses, what do you propose? Which way we can go forward?
So yeah, of course, Rupesh, you are an expert in the field, so you know the difficulties in doing this. So the way that we try to approach this issue is to try to optimize all various aspects, starting from the laser, of course, the laser line width, going to the phase locking technique. I think the recovering of the phases, the use of the pilots, compared with using efficiently potentially pulse CP techniques and digital signal processing, all of this together, by optimizing all these various aspects, I believe it will become possible to improve this transmission distance with LLO. It's a combination of factors, and I agree with you that this is not easy. Yeah, I mean, it's a current challenge in the field. I agree with you.
Thank you.
Okay, excellent, great. Then we have another question by Emina Soljanin. So here we go, please, Emina.
Hi, Lenny, nice talk and nice picture of Santorini, I guess. My question is, I would like to hear your opinion on QKD that is based on frequency time entanglement.
Frequency time entanglement. Which protocol do you have in mind?
So when Bob and Alice based their bits on the point in time that their photons arrive.
Right. So now what happens is that I don't have in my mind what has been achieved from an implementation point of view with this type of protocols. These are entanglement based and with entanglement based systems with high dimensional encoding. Is this what you are referring to?
Yes.
Yes, okay. So more globally, right, for high dimensional encoding, yes, I did say it from the beginning that I wouldn't cover high dimensional, although I know there is a big effort in this direction, and I follow it closely to see where it will lead. My opinion up till now, so this tutorial was more focused on protocols and systems that have actually achieved a certain level of maturity that allow them to be considered even for field deployment, right? So in my opinion, for the moment, for high-dimensional different encodings like frequency times, that they could be very promising, but for the moment, they are there's still some work to be done to make them more mature technologically. So I find, typically, when I look at implementations of high-dimensional systems, that there is, I'm going to put it a bit bluntly, there is a lot of effort, technological effort for performance that cannot be compared currently with other systems. So I think they could be promising, but they need more work to make them more competitive, let's say, with the other technologies. I see the potential for the rates, for example, for the higher rates, but for the moment, this can happen for very, very short distances. So why not? For example, we can think of use cases like this data center connection where we don't need long distances, but we need high rates, where such a protocol, for example, could be promising. Why not? Absolutely. I think for me, it's all a matter of making the correct link between the use case that I've tried. This is the message I try to convey between the use case and the system, the available system.
Thank you. That's nice to hear.
Okay, excellent, great, thank you. So then we have the next question is from Rodolph Schoenmarker about the media. Rodolph?
Yeah, first of all, thank you very much, Elena, for the nice talk. And I was wondering, what would be your choice of connection medium? So free space, dark fiber, or anything else from a security point of view at the moment?
For me, from a security point of view, what matters is not the medium, but the node. So what is this is for me the main differentiation. If the advantage from a security point of view of using satellite link in particular is that you can easier treat the satellite node as a trusted the satellite as a trusted node. So from a security point of view, it may give a better let's say feel more confident that your security is not broken, and if you can deal with you're okay to deal with trusted nodes, then this is the advantage of the satellite. But from the difference between dark and lit fibers that you mentioned does not typically pose security issues. This is covered by the protocol, right? So this is just implementation issues that matter. So for most QKD implementations, easier from an implementation point of view to use dark fibers than lit ones, but using multiplexed classical signals does not affect security.
Okay, great. Thank you very much.
Okay, excellent. Then we come to the next question from Raja Yehia, talking about twin field in MDI-QKD. Please ask your question.
Hello, Raja. Hey. Yeah, I can see the talk. I can see the question. Go ahead, Raja.
Yeah, if you can see the question, you can already answer. I mean, the question was just to have a little more intuition about twin field QKD, what it is and the relation to MDI-QKD. Is there any implementation of this?
Oh, yeah, absolutely. So twin field, I'm going to simplify very much, but the twin field relies on single photon interference, while MDI, measurement device independence, relies on twin photon, on two photon interference. So basically twin field, even this is how it achieves basically this extension, this improvement in the key rate with respect to the repeaterless bound, but at the same time, it's a lot harder to implement. You need a very good phase stabilization from an implementation point of view to perform twin field. So ideally, let's say the twin field does the job even better, but it's a lot harder to implement. I would very highly recommend Raja to check the invited talk for the latest distance record breaking of twin field QKD that is on Thursday, if I'm not mistaken. There is a talk that talks about 500 kilometer achieved with twin field, and there are various implementations by in Cambridge as well, and several groups that have shown the potential of these technologies.
All right, thank you.
Okay, excellent. And we come to the next question from David Shaw, please. Please go ahead.
Oh, hi, Eleni. Thanks for the great tutorial talk. What's the milestone in quantum communications that you'd be most keen to see demonstrated before QCrypt 2021?
That's a difficult one. That's a difficult one. Thank you, David. What I would like to see. Well, obviously, if we're looking at these famous high stages of the quantum network, the more complex functionalities that we can see performed, the better it is, right? From this point of view, I would like to see implementations that show scenarios where we, in real life, okay, with actual deployed systems, we can manage to perform some functionality that include QKD, but also other type of applications like delegated computing or this type of more cryptographic and distributed computing protocols. So this would be nice. I don't know if it's possible for 2021. Other milestones that I would consider is that systems like the ones that I presented, all 4 configurations, for example, that I highlighted, performing together in this type of deployed fiber network. So this would be very nice, a very nice outcome, a very collective as well outcome of the community to show that it's possible to perform in an integrated way in both ground and satellite networks this type of functionality. This would be a huge step ahead, I think, to demonstrate the actual maturity of this technology.
Okay. Excellent, Kate. Thank you. And then we have a question from Gilles Brassard. Gilles, please.
Yeah, Evkaristo, Eleni, great talk. In one of your very early slides on performance measures and use case criteria, what is the right topology for QKD network? You made a connection that I did not understand between prepare and measure schemes and trusted nodes, as if the trusted node scenario required prepare and measure schemes. I don't see the connection.
No, I think it was the opposite that I was arguing, that when you implement prepare and measure schemes, if you do want to extend the distance and you cannot do it, your system does not allow you to go beyond, I'm going to just say an example, 100 kilometers, then what you can do, the solution that you have will necessarily include somewhere a trusted intermediate node. This is the argument that goes that way, that if you have prepare and measure schemes, you need to do trust node to extend the distance. Now, that doesn't exclude at all that you may use other obviously protocols and you still trust your nodes, obviously. So this is the direction I was going. You see what I mean?
Okay, I was reading in the other direction, sorry. But still, even with prepare and measure nodes, schemes, I mean, why can't you use a repeater, untrusted repeater that would sorry.
I think I see what you mean. I think I see what you mean. If maybe we can work the question together. I think what you mean is that, say that we do have a quantum repeater, and so this issue of upgradability that I mentioned, that we do want to have quantum repeaters and other protocols, but we also want to include prepare and measure schemes. I think this is perfectly doable. It's just that we need to somehow in our network separate the functionalities that rely on prepare and measure schemes and the ones that rely on entanglement-based, for example, systems, on relay-based systems, let's say.
Right.
So it's possible for them to coexist. This is what I think, and I would like to see this happening actually, and I think it makes sense. But it's possible for them to coexist, but not immediately use exactly the same node technology. That's what I meant.
That's right. That's right. We require better technology for that. Okay, thank you very much.
Okay, perfect. Then we have a last question from Zhang Zhang. Zhang, please.
Oh, okay. Thank you. Hi, Eleni. It's a very nice talk. Hi. Because you talk about the QKD beyond, so I just want to know what do you think the next killer application except for QKD or besides QKD in quantum crypto?
Almost as difficult as the question of David earlier. So if I knew the killer application, I would do it. And so it's difficult. Again, it's difficult to answer this question. I think I tried to give among the in this list that I showed among the different applications. It's a list of functionalities, okay? So it's not a killer application; it's a functionality that all of these that I showed, you know, in the graph with the applications beyond QKD. I cannot pick one of them right now and say that this will lead to the killer application. I think if we take quantum communication largely, that's why I'm insisting on it. Implementations that can perform functionalities like the one that we saw, oblivious transfer or the coin flipping, and also these delegated or blind computing things where you use quantum communication with some client and some server to perform quantum communication in the larger sense, or where you build upon as well your QKD technology, is the one that will be probably the most likely to have some impact in the most general quantum information networks. Consider them more widely. It really depends on the use case. For example, I find interesting this anonymous the anonymous message transmission protocols that we have used. I think it can be useful. We can think of leader election, all these type of primitives that are actually used in classical networks that could be extended to the quantum realm. And I'm also going to emphasize here specifically for QKD, but also for other protocols, that we should not ignore at all the importance of comparing, of integrating with classical solutions as well, post-quantum or other solutions. So I find this extremely important as well. We should not forget how crucial it is. Then there is all this wide range of functionalities will eventually lead to the killer app. I don't want to pick killer app as it is right now. I don't think we should. I should.
Okay, thank you. And about the question from David, I think if we have time, we can go to the lab. I think probably DI-QKD will be something. Yeah.
Good. Okay.
I guess so. Yeah, but yeah.
Okay.
Looking
Excellent.
forward.
Great. Excellent. Thank you very much. I think with that only coming to the end of this session. So I really would like to thank Eleni again for this really nice presentation, the excellent overview, and really showing us the whole breadth of kind of questions that are coming up, things that we have to think about, and as well to look at the potential of our applications. Thank you very much.
Thank you. Thank you very much.
And with that one, I think, Eleni, you will be as well available in the coffee room, or or do we have to come to your beach right now?
No, I'll try to go to the meet and greet room. Yeah.
Okay, excellent, good. So then see you all in the coffee room, and then the next session is starting at.
We will start in about 20 minutes.
Yeah. So then we have to go quick to get our coffee.
All right.
Okay.
See you
in
there.
the coffee room.
Yep.
Thank you very much.
Thank
Bye.
you.
Okay. Okay, I think we'll start the session. So good whatever part of the day you're in, and welcome to today's invited talk. Today's speaker will be Félix Bussière from Idées Quantiques and the Université Genève. He will be talking about recent work that resulted in speeding up QKD, and also, as in the second part, how to downsize the quantum random number generators produced by Idées Quantiques. Before going to the talk, I would just like to remind you how we proceed for the question and answers. So you can ask your question and answers in the question and answers sections, and we will ask those questions at the end. So we'll be left with 10 minutes for answering these questions and answers. You can also raise your hand, and you select the way you want to proceed. So okay, so we're now ready. So Felix, if you're ready, we can start.
Yes, you can hear me?
Okay. Yes, very
Excellent.
good.
Okay.
Thank you very much. Good.
Thanks, Louis. Thanks to the organizer for this opportunity to talk about these two topics today. My name is Félix Bussière. I work at IDQ and at the University of Geneva. And I have quite a generic title, but I'm going to jump in a bit more details right away. There's going to be two parts in this talk. The first part is really about how to speed up QKD. And I want to focus here mostly on the detector part that was used in some recent experiments. That's going to be the first part. And the second part is going to be about IDQ's QRNG chip, and with a focus on its security model. Okay, so let's just jump in already in the first part here. There's been, for many years now, there's been a lot of QKD work being done at the University of Geneva in the group of Hugo Zbinden. Now, since 2014, there's an activity in the SNSPD part, and naturally the goal is to develop some detectors for the requirements of the experiments happening there. So this is, I want to talk about this, essentially how we've been using these detectors to satisfy the needs of the QKD experiments and also other experiments, but I'll be focusing on the QKD part right here. Okay, so this, for a couple of years now, there's been a workhorse system that's been used at the University of Geneva for doing QKD, and this system is using the BB84 protocol, 3 states and 1 decoy. My focus here is not on this, but I'll briefly go over it so that you have an idea of how it works at a high level. So the idea here with this system is to be resource efficient. Okay, what I'm going to activate the laser pointer. Hopefully you can see that. Louis, can you see the laser pointer? Oh, okay, excellent. So the idea is to have a resource efficient approach. So by reducing the number of states in the protocol, and then also by using only 2 intensity levels, 1 decoy, you can also minimize the requirements on the hardware. And hopefully, if this ends up being deployed in a large number of systems, then you can have some minimization that can be quite useful there. So the idea of the protocol is to use these 3 states here, 0, 1, and plus. It's a BB40-like protocol. It's encoded into time bins with the 1 time bin here and nothing there is 0. This is the 1, and here you have the superposition of the 2, which gives the X state. The security of this protocol was proven in this paper here. And actually, the 1 decoy approach is interesting because it actually provides, in some regime, the ability to increase the key rate with a non-negligible percentage level, and that was shown in that paper here. So in practice, you have an Alice, you have a Bob. So Alice has a pulse laser, an interferometer to create the time bins, intensity modulation also for the time bins and also the decoy states, some compensation for fiber dispersion, a variable attenuator, and on Bob's side, there is an interferometer for measuring an X basis and a detector to measure in the Z basis. Back in 2018, the goal with this system was to go towards very long distances in optical fiber. So in order to achieve this goal, we developed some SNSPDs that have the potential of having very high efficiency and very low dark count rate. And actually, we achieved a dark count rate of 1/10 of a hertz with about 60% system detection efficiency, which led to QKD over 400 kilometers. So that's not very recent news. This was presented 2 years ago in QCrypt. You know, it's an interesting result that was attained thanks to the development on the detectors. And since then, other groups have demonstrated QKD over even longer distances using the twin field approach, for instance. Okay, so the next target for this system was to go to high rates at shorter distances. So a bit more details about this system. The repetition rate is 2.5 gigahertz. The pulse durations are 30 picosecond, and then intensity is modulated at 5 gigahertz. And in order to achieve high rates, you really need to work a lot on the post-processing part. So the sifting actually is able to deal with up to 200 million detections per second, quite a lot. The error correction can operate at up to 100 megabits per second. And the primacy amplification is geared up so that it can, in principle, generate up to 60 megabits of secret key rate per second. Okay, so quite a beefed up system. Now, in order to achieve this potential, you really need to work on the detection part to achieve this. Okay, and that's what we wanted to do here. And then in order to achieve this, we had to work on a new breed of detectors. We really wanted to have something that could go high up there, but still keeping this resource efficient approach. Because one way you can do it, you know, you need to beat the recovery time of the detectors. So one way you can do it, or you can try to do it, is by essentially putting a lot of detectors in parallel, either with beam splitters or multi-pixels and so on. But at some point, you know, if you want to have 32 detectors or even more, you're going to have some other constraints to deal with, which is the time processing, the time tagging, and the time processing that you need to input there. You're going to have to also increase the cooling power of your cryostat. We wanted to keep things relatively simple, a relatively low power cryostat with a small number of detectors in order to have something realistic that can hopefully be deployed in different locations without having too much cost into it. So we worked on the detector part in order to achieve something that would approach these requirements here. So in a nutshell, I'm not going to spend a lot of time on this, but SNSPDs is an activity that started, as I was mentioning, in 2014 at the University of Geneva. We are working with molybdenum silicide SNSPDs. We're making them directly at the PFL in Lausanne. And the operation principle is the following. You have it's not a nanowire, it's more like a nanostrip, something very thin and relatively wide. We're still talking about nanometer scale devices. You have this superconducting material, you cool it down to below the critical temperature and you bias it below the critical current. And when a photon comes in, it's going to break a large number of Cooper pairs. So you weaken the superconductivity here, and then the bias current interacts with that and creates a resistive region. When you bias the circuit, the detector in a circuit like this, and the detector is modeled like a kinetic inductor in series with the resistance either 0 or something of the order of 1 kilo ohm, the current goes in here, and when it switches, it's going to leave that branch, go into the amplifier, it's going to create this very sharp rising edge right there. And then when it becomes superconducting again, because there's no more current in it, it will more slowly be rebiased by the current that's coming back, and the dynamic is governed by the ratio of this inductance over either this, something large, so quick unbiasing when you have a detection, and then it's slowly coming back because the dynamic is governed by this resistance here. So this LC circuit is rebiasing more slowly. So you get a pulse like this. Now, if you want to detect fast, you need to have something fast enough, but there's a limitation. You need to cover the optical fiber surface with this, so you have a certain length that will affect this kinetic inductance right there. And then if you try to operate at very large detection rates, you may be faced with latching. Latching is a situation where the detector gets stuck in a permanent or semi-permanent resistive state, and the only way to get out of that is to take the current back to 0 and then back up to the value you want to operate. And if you want to do a QKD system and you end up in this latch state, that's not going to be allowing you to go to faster speed. So how do you get beyond that limitation? Well, we wanted to try the following, and the idea was inspired from photon number resolving SNSPDs, which were demonstrated as early in as 2008. The idea is intuitive. Instead of having this, you take your area and you divide it into several sections and you connect them in parallel. So something like this here. So each of these is one of those pixels that you see there. There's 3 here and 4 there, but you see what I mean. And intuitively, you'd say that if you have one detection here, this becomes disabled, but the other ones are still there to actually detect. So you have a couple of detectors in parallel available for detection, and you can perhaps hope to have a greater detection rate there. The other benefit of doing that is that each length is shorter in distance, in length, so you're going to have a smaller kinetic inductance, and you can hope to have everything working at a faster speed. There's a limitation, however, which is crosstalk between these different pixels. So when this becomes disabled, the current leaves that branch, and the other two are going to pick up the leftover along with the readout. And therefore, if you operate very close to the critical current of each of these sections, then you may actually force these guys to click as well. And if everything clicks simultaneously, the whole thing is going to reach a latch state. So that can be a real problem. So this electronic and also thermal crosstalk, you need to take pay attention to that. So we wanted to try this, and actually we knew this wasn't going to work, at least with our preliminary test. And moreover, this idea of counting fast with these parallel detectors was not found in literature so far. So we tried the following strategy. We had to be a bit clever to allow the system to mitigate this crosstalk. And the idea to actually achieve this is by adding on chip something else that's going to absorb the extra current, so that it's going to minimize the crosstalk between these two. And actually here I'm showing one extra wire, but in practice it's a lot more. It's, if you have let's say 8 pixels here, you can have as high as 40 or the equivalent of 40 nanowires outside of that. So it's as if you have a lot of nanowires to absorb the crosstalk, so then you're not going to be impacting the other exposed wires. Now, these are exposed to light, and these are not exposed to light, and that's the trick. Another trick as well is to make them wider so that if everything clicks, not everything is going to be, well, everything is going to go there and in the readout circuit, but not everything is going to be resistive, so the whole device will not necessarily latch. So you can opt to be able to go to high detection rates. Now there's a trade-off, of course. You don't want everything to go in there and not in the readout, because you need to have some part in there and some part in the readout so that you can have a signal at the outside that you can still discriminate. So it's a matter of really playing with the design. There's lots of parameters to tweak, and we managed to make this work. If you look at an SEM image of the detector, it looks like this. You have this section there, which is divided into 8 sections that are exposed to the light. Everything around is not exposed to the light, so they cannot click because of light. And then here you have a couple of detectors. Each parallel nanowire here outside, these unexposed ones have their kinetic inductance and then their series resistor. So how well does it work? So if we compare to a single, let's say, classic SNSPD, here we're taking one that is rather slow, but still it increases the dramatic effect of having something that's better, but still it's not too far from the best ones that you can actually get. You're going to have a system detection efficiency that's going to be decreasing as the detection rate increases, because you hit this recovery time there. And if you see something here that starts around 80%, it's going to go down at some point. And here for this nanowire at 10 megahertz detection rate, you have a pretty big hit on the efficiency there. So how do you get rid of that? Well, we try this approach with these parallel nanowires, and actually you can start still with a very good efficiency, close to 80% at 1550 nanometers. And then you can look at how far does it go. Actually, for this one, we can still detect at 100 megahertz with CW light at the input. So random times for photons arriving, which is the configuration that looks the most like a QKD system. And we have this very good, we don't take a hit. Actually, this detector is not able to count at 100 megahertz at all, but this one can. And then there's no latching effect. You can crank up the power and don't have latching. So that's good. It's a good sign that we can use this in a QKD system. In a QKD system, you need to operate it mostly in that regime. You don't want to take too much of a big hit on the efficiency. And the jitter is between 60 to 100 picosecond. I'll be talking about that a bit later. And the dark count rate is about 100 hertz or less. You can play tricks and try to lower that as low as 10 hertz or even less. Now, to demonstrate that this actually works, we also made parallel SNSPDs without the necessary protection mechanism that the other nanowires around. And if you operate these close to the critical current, then you're going to count. And at some point, they have a high probability of latching here at 20 megahertz. So to get rid of that, you can lower the bias current so that when you do have this electronic crosstalk, it's not going to be impacting too much the other ones. But by doing that, you lower the efficiency. You can count faster, up to 100 megahertz here, but you have an impact on the efficiency. So that really shows that there's an advantage with this approach that we have. So there's latching and you have a lower efficiency. So putting all of this into the QKD experiment looks like this with 50 kilometer of ultra low loss fiber and an attenuation of 8.7 dB. We've been able to achieve a raw Q rate of 27.8 megabits per second and a secret Q rate of 8.7 megabits per second, which is a very good result for this distance here and that amount of loss. We can lower the loss and achieve a higher rate. But we're not, as you can see, we're not achieving the electronics or the full potential of the system there. So there's still some work to do on SNSP. This was with 4 detectors here. There's still some work because there's still not a drawback, but there's still a limitation with this approach, which is the jitter. If you have too much of a jitter, you're going to have detection spilling over in the next bin, and that's going to increase the Q-burr, and you're not going to be able to do QKD anymore. So this jitter actually does increase with the detection rate, which is a limitation of any SNSPDs, because the jitter of an SNSPD decreases when you decrease the bias current. So when you start hitting the recovery time of your detector, you're going to take a hit on the jitter. So that's the limitation that we have to deal with right now. And there's, the way forward to realize these 50 to 60 megabits per second with such detectors is really into optimizing the design, optimizing the material, and hopefully get to 25 to 50 megacounts per second with at least 50% efficiency, but I think we can do better here, and deal with this jitter stability problem. And then, of course, you can increase the number of SNSPDs, but if you put 8 detectors, each having 6 or 8 pixels in parallel, then you're going to end up with a machine that doesn't have too many coaxes and inputs to time tag, but still have a lot of power for operating at high rates. Okay, so that comes to the end of this first part. I want to say big thanks to everyone at the University of Geneva, the QKD and the SNSPD team. And the results, the detector result that I just mentioned are submitted. They're going to be appearing on the archive soon. Okay, so that brings me to the second part of my talk, IDQ's QRNG chip and its security. So IDQ, you may have heard about this. IDQ has now a chip that does quantum random number generation. And the goal is to disseminate it into many devices. And IDQ wants to offer a path to quantum security to the people buying its devices. Now, ideally, we'd like to have QKD everywhere, but as you know, QKD is still rather expensive technology. It's still bulky, so it's not something you can put everywhere. It's not for everything at the moment, but there's still a path that you can take that can, in the future, lead to have the maximum security that quantum technologies can actually offer. And this path is first by using a good way to generate your random numbers. So the QRNG, we believe, is a good way, and that's what I want to talk to you about today. And then you can, Alice can generate a good random key and then distribute that to Bob using a post-quantum algorithm, which is believed at the moment, at least not shown to be insecure against a quantum computer. And then for some situations where you need long-lasting security and then the budget is there to actually accommodate it, you can go to quantum key distribution. The nice thing as well is that this chip here is small, so low power consumption, so you can actually put it in a QKD system that also will reduce in size as time progresses. So why do QRNGs help? Because they're not the only kind of RNGs out there. So QRNGs help because we believe they do, because they offer a clear and robust entropy generation mechanism with the security tool. And that's really, I think, the extra you can get with such devices. What do we need to make them ubiquitous? Well, you need low production costs for mass market. So CMOS IC compatibility is a plus, which is the case with these devices. Small footprint, low power consumption, and you need to have some compliance with security standards such as FIPS, NIST, or common criteria AI is talking about. So the idea behind the chip dates back from a paper in 2014, QRNG on a mobile phone. And this paper made the realization that essentially all the cell phones in 2014 and still today have a camera that is able to see the fluctuations of light. Okay, so a CMOS image sensor is at the basis of everyone's cell phone camera, and each pixel is essentially a very, very good photodiode with high quantum efficiency and low noise. And then you have an amplifier, so you take photons and you convert that into electrons that carry the entropy of the photons here, or the photon number statistics, and then you generate a voltage, put that into an ADC, and you have a bunch of bits here that will be impacted by the randomness of the input right there. So each pixel in a camera is rather slow, but you can put millions of them, as you know, and therefore you can parallelize the whole thing, and you can hope to get some good rays out of that. Okay, and so the industry compatible elements are there. So in this paper from 2014, an LED, which is a multimode thermal source, which is yielding a Poisson photon number distribution, was shown onto a camera. And if we look at one of these, for instance, from the Nokia N9 phone that was used back then, this produces after the ADC a code. It's a 10-bit ADC, so it produces a number between 0 and 1023. And it produces a distribution. And the distribution you see there, if you just put it back towards 0 for looking at the width, and you compare that to the noise that's coming out when you have no photons at the input, you see that the distribution is much wider. And actually, this distribution is directly given by the photon number statistics that you have you are producing from the LED right there. So that's already a very good indication that you do capture the randomness that you have there. So you produce this 10-bit ADC. Now, it turns out that with the code size and the intensity, you want to work in the right regime, and you're going to produce a code. So it's kind of like you draw one of these numbers at random. And then in this 10-bit ADC, well, the most significant bits are not going to fluctuate a lot. Actually, they don't carry entropy. They're very predictable. The least significant bit varies a lot, of course, but then it can be influenced by the classical noise that you want there. So actually, it turns out that these are the ones that vary the most. And you can prove that here you have about 5.7 bits of entropy. Now, if you want to get a high entropy output out of these 10 bits, you need to run it into a randomness extraction, which was done outside of the phone. So it's not yet a format that allows to directly put it into a chip. There's still some work to do outside. And one trick to make this happen is actually to realize that you don't need all these bits. You can just keep bits number 2 and number 3. Okay, so you don't need to use all of it. And that's what the IDQ chip does. Okay, so the design and so on has been going on for many years. It's now available commercially. And the idea of the chip is the following. You have this CMOS image sensor dedicated for the generation of random numbers. It's, again, a Poisson statistic source. It goes to the ADC. You keep bits 2 and 3. And you have your quantum entropy directly at the input. And the input distribution is this one here. There's also a DRBG for dealing with potential remaining bias there, but I'll be talking about this a bit more later. But I just want to focus on the quantum entropy right there. So these 2 bits here, if you want to convince that it's going to give you a high entropy output without having to do any extraction, well, you can look at this distribution here. So from edge to edge, it's about 100 ADC codes, okay? And keeping these 2 bits only, it's as if you're going to produce 2 bits, and you're going to flip which one of these bits that you actually keep every 4 codes. So 50 to 53 is going to output 00, 53 to 57 is going to output 01, and so on. So all the green ones output 0, all the red ones output 01, 10, and 11, and so on. If you take this whole thing and you kind of put it there, and you try to see if everything is exposed uniformly, then you actually realize that it is. But you can make this more formal, of course. I'm going to show it. But essentially, that gives you already an indication that you should be able to provide high entropy output out of that. So Let's go into the physics of each pixel a bit more. You have this photon number distribution. Here you have some loss. Loss is just a beam splitter. It only decreases the mean number, but you directly transfer these statistics into the number of photon generated, and you can have some dark electron noise. So also having a Poisson distribution, you're going to add these two together, and you get a total electron number that goes into a conversion. So you want to convert each electron into a voltage. So you do that here, and by doing that, you also add some Gaussian electronic noise. So you have a voltage here, analog value, quantum plus this noise there, and you feed that into an ADC, which gives you a sequence of 10 bits. So there's an effect here that is subtle, but it's important to mention. You have some pileup of the ADC code. So if you look at the whole process, this machine basically transforms one electron or a couple of electrons into ADC codes, and it's not one-to-one. And actually, in most of the cases, one electron is going to be just a little bit less than one ADC code. Okay? And that's why, so if you have that, so this conversion factor here is a fraction of one ADC code step provided by one electrode. Okay? And of course, the ADC is going to be doing some quantization. So if you have one electron, you may hop over the ADC code. The second electron you also hop over, but the third one, it may not be hopping over. So you're not going to be increasing the ADC code. So that gives rise to this pileup there. Okay, so that's a classical simulation. No, sorry, that's a simulation of the device that we should be seeing with the actual measurement. So is that a problem for entropy? No, because of the way, because of the fact that keeping bits 2 and 3 allow us to still have a fairly uniform distribution of the different 2 bits output. And if you just measure it, you get something like 1.964, which is very close to the maximum you can get there. Now, you also need robustness to light intensity and non-uniformity in the exposition. Of course, you know, like not every pixel is exposed or illuminated the same way. So if you, again, run a simulation and you make sure that the intensity is in the right range, that is not underexposed or overexposed, in this right range, you have a flat section where the entropy is near optimal. Right? So let's go have a look how it actually works in practice. So here we see 4 pixels on the CMOS image sensor. You can see that they don't have the same mean value. This is more like 550 and 450 here. So we do see the pileup effect, which is expected from what I just explained here. And it does look consistent with the Poisson distribution. As you know, a Poisson distribution, the mean is equal to the variance, so it should get wider as you increase the mean there. So to verify this, you need to take into account the conversion given by the ADC, so that translates it into a variance that varies like something that's proportional to the mean value plus an offset of ADC, and that's what we see there as expected. So we're comforted in the fact that it looks like it's working like as it should. Now, what about the noise? If you switch off the light here, you're going to be left with a small distribution that's like very close to 0. This one here, mean value around 10 or so, and you have some structure into it. And actually, you kind of see the periodic structure of the pileup effect. That's normal. That comes from these dark electrons there. So you don't have these, you have only that. But these also contribute to this pileup effect. And that's smeared out with a Gaussian here. So you have this shape here. So you can try to fit that, fits very well. And you get the values for these here. And you can know how much noise E can exploit. So this side information is something that you want to know how much it contributes to. So intuitively, you can just like look at this and imagine how much this can allow Eve to guess which of the codes here you're going to get. And actually, it's not a lot, but you can make it formal and calculate this guessing probability. So the way to go is written in this paper here. So you take that side channel information, you see how it affects the probability of getting one of the codes, and you calculate the min entropy there. And you put all of this into a graph where you look at the region where the intensity of the lead is found, and you see that it's pretty flat. Over the whole useful range, you're going to get a min entropy of at least 1.95 that you have at the output of it. So we're near optimal, actually, and then everything fits. So we know the device is working properly. There's other checks that need to be done, like correlation between pixels or subsequent frames. We have done that. I'm not showing them, but we haven't found any correlations like this, and that's normal, and that's from a mature technology such as CMOS image sensors. There's also an automatic failure detection mechanism, and actually it's interesting because this detection mechanism would fail before the entropy decreases. So if 5 years after the chips for a reason fails, it will not give you bad entropy before failing. It would just fail, but it will have good entropy until it fails. So system level view looks like this. There's this DRBG there. So the DRBG is necessary to get certification in a secure application. So some people will want to have that, or some people will just take the quantum entropy and do that outside. If you want to do it, it is there, and you can get certification, security certification because of that. The architecture is compliant with NIST and AIS-31. It has integrated and live health checks with physical protection. Of course, if you shine light on the chip, it's not going to be seeing that light. It's all completely blocked. It works in a completely autonomous way with auto calibration and entropy source or DRBG RNG data if you want. Operation modes can be in terms of size, the smallest chip is 2.5 by 2.5 millimeter in size. It's pretty small. The biggest one is 4.2 by 5. The entropy rate of the biggest chip is up to 20 megabits per second, a very good rate, and it's necessary for pretty much all the applications out there at the moment. And the power of the smallest chip is as low as 50 milliwatts, and then you have a power down node of 100 microwatts. So it is suitable for small handheld devices. So I'm not going to show the entropy test result and randomness test. We max out the outcome of the NIST 890B IID and non-IID test suite. Randomness test, we passed the test 822 and die harder with the expected rates. And both of these in varying environmental conditions. One of the chip has this automotive certification, which guarantees functionality in harsh environments, high temperature, low temperatures, and so on for the automotive sector. There's many applications for these, but I want to talk about one, which is the mobile phone. This year, IDQ, a Samsung collaboration with SKT, released a phone that has the QRNG chip in it. It's a Samsung A series phone. It's called the Samsung Galaxy Quantum. It's available for now only in South Korea. Hopefully, this chip is going to be available everywhere now. But it's we're very excited by this outcome there. It really seems that quantum technologies are making it out there, and I think in the next 10 years we're going to see a lot more of this. There's in the system, there's some applications that use that, payment services, cryptocurrency services, very popular in South Korea, and also some identification services, which benefit from the randomness of the QRNG chip. Also recently, IDQ just announced that there was another company that is going to be using the QRNG chip in its cell phone series. It's VinSmart in this Aris 5G smartphone. So hopefully more and more of devices will be using those. Okay, so there's a growing number of technologies, but I covered only these two here. What's important here is to have this, one of the things that's important is to have this clear and provable security in order to be able to use this in that. Okay, so that concludes the second part. I want to say thanks to the people who worked on this, Gaetan Graj and Wen Choi, Anthony Martin. And then there's a publication that's going to be appearing on the archive pretty soon on this topic. Okay, so that brings me to the conclusion. First part of the talk, I spoke about SNSPDs tailored for fast QKD. We were able to speed up our SNSPDs and achieve 8 megabits per second of secret key rate at 50 kilometers in ultra-low loss fiber, and we're working towards having much higher secret key rates. And then I spoke about IDQ's QRNG chip, talked about the detailed model of the entropy origin, and then the fact that we have near optimal entropy with the proven security and robust operations. And it's nice to see that these devices are now on cell phones.
So with this, I conclude, and I thank you very much for your attention. Louis, I think you're muted.
Okay. Thank you very much, Felix, for this very nice talk.
Thank you.
Okay, so we're now ready to go and see the questions. Okay. Toshihiko Sasaki has a question. So now I have to find out if I can. Where is the participants?
Thank you for very much. Very nice talk. So,
okay. Oh, good.
Okay. Okay. So yeah, as for QRNG, intuitively, so your model is attenuated single photon, so it has some coherence. So intuitively, I agree with your model. But for example, random number cannot be checked from output. So we consider the origin of the entropy. So in this sense, I'm curious about how third party can check this device. So we can see the Poissonian distribution. Maybe that is not enough for. So how can? So I'm just curious.
Yes. Okay. So you can. There is a okay. Right now we don't have a machine that you can just buy directly from us that allows you to check it. Although it's possible in principle, so it's possible to access the chip and then talk to it in such a way that you can control all the features. And you can, if you want, play with the intensity of the LED. You can switch off the LED and reproduce all the measurements that I showed here today. So all of this can be done on your end by having access to control of the chip and taking out the measurements. That's what we did. We just have this machine that allows us to control. We got the measurements. We didn't have to open the chip or anything. We just plugged it in and gathered the results and produced the data that I showed today.
But
does that answer your question properly?
If third party, yeah. So if third party does not believe your device, so maybe they random sample that and maybe check some devices, and in that sense, how they can check that. So maybe we will discuss later. So if other questions, so
yeah, with pleasure.
Yeah,
with pleasure. I'll be happy to do that.
No, thank you. Okay. Devda Sharma has a question. So maybe we can give him the let's see. Whoops. Where? How can I get participant? Spectator. Dev. I'm sorry. Okay, I'm going to unmute Devda Sharma. Okay. Whoops. Okay, you can ask your question.
Hello.
Hi.
Okay, hi.
Hello.
Yes, we can hear you.
Hello.
Hello.
Hello. Can you hear me?
Yes.
Yeah, we hear you.
Yes, sir. I want to know that can we use this random number generator for banking system like password system? Banking password type.
To generate a password, you mean?
Yes, for banking transfer of money like that.
Yes, absolutely. Any transaction that requires a transfer of confidential data can benefit from the QRNG, from the good randomness that you get out of it.
Yes. Thank you, sir.
My pleasure.
Okay, so I have another question from Jing Yan Hao. I'll try to. Okay, so I'm going to unmute Jing Yang Hao. Converser. Oh, no. Well, I'm sorry. I mean, okay, here. Good. Okay. You can ask your question, Ying Yan Hao.
Yeah, thanks, Luis, and also thanks, Felix, for the nice talk. Yeah, indeed, I think it's good to bring the QRNG down to like really smaller level and then accessible. I think it's definitely a good approach. So I have two questions here that I'm curious. Yeah, it's good that the whole random extraction is being simplified to the process of like taking the LSB. I think it's not very super rigorous, but I think it's practical. My question will be, when you say about passing needs tests, right? Are you referring to, so you also mentioned that there's an option where the user can use without the hash-based DRBG. So when you the test, is it prior to this unbiasing or afterwards?
So I'll try to, can I easily go back to the slide without, I'll just go like this. Okay, so so your question is there any, well, okay, let me just go through it again and make sure that I explained it properly, so maybe that would answer your question. So the output there, as I explained, is this this set of random bits that go here, and this is just providing entropy bits. And in a security application, you need to have entropy source. And so this whole thing is the physical entropy source, quantum entropy source. And then this, in a security application, to get certification of the whole thing needs to go through a DRBG. That's just how the security standard is at the moment. Okay, so this part here is necessary. So it does unbiasing. Actually, if you start with a low entropy input, this will give the appearance of increasing the entropy at the output. However, if you start with the already a very high entropy input, this is only going to give you something that has less bits, but you cannot max out the entropy a lot more. So does that answer your question?
Yeah, so partly, yeah, I understand that. So after because it's the deterministic case, so in principle, yes, it shouldn't increase the entropy. So, but what I'm wondering is that at some point you show that with taking those two LSB, you can already see that the distribution is somewhat uniform. So yeah. I'm just wondering whether, you are already using, let's say, without this certification, can one already use it as random bits, for example? By random, I mean uniform, and also So
your question is if you take these bits here and feed them directly into the most rigorous test, such as 822,
yes, that's right.
22, does it actually pass? And the answer is yes, it's going to pass. There's a little difference, but it's not, it's very small difference. So it does pass it actually.
Okay. Yeah.
But still, you know, in a sense, if you want to, the current state of things is that if you want to get a security certification, you have to use the RBG. So, you know, from a security point of view with certification, you have to use it, the RBG. But in principle, you could actually bypass it.
Okay, I see. Yeah, thanks. And that actually leads to my second question. So you also mentioned that you have done some mean entropy. That's also conditioned on the classical noises and so on. Yeah. So I'm just wondering if this, and then you also mentioned if something broken, and then it will probably still work on or guarantee until, I don't know. Yeah, I probably missed that part. But I'm just wondering, is the mean entropy estimation done, let's say, once at the factory, and then, or will it be checked, let's say, every now and then, or if there's a button where the user can press and say, okay, recalibrate my mean entropy, and then,
so it's both actually. So it's done, of course, in the factory, but then at the in the chip itself, there is a lightweight entropy health checks that is being done live. So if this gets derailed, then you're going to get an error status popping up. So that's necessary to ensure the good. It's one of the health checks that is being done there. However, the retesting the entropy the same way that it's done in factory, you can't on the chip. However, you can, because it's too computationally demanding, but you can just output the bits yourself. If you want, you can embed the chip into a system and just sample and then do this live check yourself, continuously run the entropy test the same way it's done in the factory and in the way it's done in the standard of NIST 890B.
Okay.
Either IID or non-IID track.
I see. So you mean the, okay, yeah. Okay, maybe, yeah, I'll probably leave, I'll probably talk more afterwards, yes.
Okay.
Yeah.
At the meet and greet room, good.
Thanks.
Vadim Makarov has raised his hand, so I'm going to, okay, I think Vadim, you can talk, unless I'm...
Hi, Felix, very nice development. The question about QRNG. So in this quantum entropy stream that is available off the chip, do you specify what is the randomness content of the stream? Do you specify that it might have a certain non-random fraction? Or so what is inside this ADC and filtering? Do you run some sort of hash function compression, or does the quantum entropy stream contain possibly a non-random component?
Well, if it gets out of the rail too much, then there's this help status that is going to pick it up. And I'm sorry, I don't have the exact details of that. That's something we should discuss afterwards, just so we can dig into that. But I think one of the things I wanted to mention here today is that by the way it works, and because of the way you actually continuously monitor different parameters of the image sensor and the output bits at the physical level and also at the entropy level. It's a lightweight check, as I mentioned, but you still do it. And also because of the way the chip works, I was showing this here, the intensity can drift on one side or the other, and you're still by design guaranteed to output very good entropy. And that's what I wanted to really emphasize here. And if it gets too close to the edge, then the chip is going to notify, recalibrate, and if the problem happens again, it's going to be stop working, and it's going to tell you that there's a mistake going on, there's something wrong going on with the chip. So there you do have these checks, physical and mathematical checks of entropy happening in real time inside the chip.
Okay, I guess my question is, if you want a perfect random stream, do you need to run post-processing?
So perfect random. Well, okay. What the NIST 822 standard does, or statistical test suite does, and a die-harder as well, it runs an hypothesis check, an hypothesis testing procedure. So it looks at the output and it tells you if this is consistent with having an actual truly random source. Okay, so when you do that with the entropy right there, you have, of course, there's always some probability of failure that's intrinsic to the device, because a perfectly random source can once in a while, with a certain probability, output something that's not going to look random, and there's no way to tell. So you have to look at the rate at which you pass these different tests, and if you run it right there, you are going to pass with the appropriate rate. Now, if there's any unbiased, there's any remaining bias happening, you're going to be getting rid of it using this hash-based DRPG. So the important point is really that the device is made so that you have all the checks running simultaneously, so that you don't have to continuously run this. This 890B, sorry, the 822 randomness test is very computationally demanding. You cannot do that on the chip. You cannot do that on a small device running on battery. So the important point is to show that the architecture is simple enough so that it will not be in a situation where it's not failed and not producing good entropy. And that's what I tried to do during this presentation. Hopefully I was able to show you that this is actually the case.
Okay. Okay, I think we're pretty much done. But maybe may I ask a question for because there are no more questions and we're getting at the end. I mean, it's the dummiest of all questions. Is there something that prevents developing a random number generator that would achieve the maximum mean entropy, because you are at about 5% of the optimal for 2 bits? Is there something fundamental that could prevent that says that no implementation could have a maximum entropy without private simplification or randomness extraction? Would it be possible, or is it impossible? Is it proven impossible?
I have no idea. It's a very interesting question. Would there, is there any no-go theorem to show that physically you cannot do that you cannot get randomness? I don't think so. I don't think quantum mechanics, for instance, says anything about that. But maybe there's something we haven't seen or don't know yet.
Yeah, because 5%, I find it amazingly close. I mean, I wouldn't have expected something like that.
Actually, maybe I can say something about this.
Yes, yes.
My guess is, of course, I know nothing about experiments, but pretty much in any experiment, whenever you use it, you're going to have a very small error rate. Let's say 5%. Maybe it's going to be a little bit lower, but it's always going to be constant. Given, like, if you use it n times, then that error rate is not going to go down with n. Right, so you're going to have some epsilon times n error, and then at this point you're going to have to do hashing anyway to get rid of this, right? Because you want the error rate to go down lower than that.
Unless you have a way to get rid of it somehow by I don't know.
But it's never going to scale with n, right? Like, it's always going to be some very small constant. You might make it very, very small, but then it's never going to scale. It's never going to go down with n. Right?
Yeah.
So I think hashing is inevitable because of this, but yeah.
Okay, so I think we're done. So thank you very much, Felix.
Thank you.
And the one who wants to talk further with him can go to the meet and greet room.
Yes, and indeed, actually, everybody is welcome now to join the meet and greet room, because that's also where we hold the poster session, which starts the first poster session, which starts right now. So everybody's welcome to move over there and walk around and have a look at the posters. Most people have, I think, set up their posters. There's a whiteboard where you can actually look at the posters, and there's always a backup option if that doesn't work. The PDFs of the poster are available from the website as well. So you can also just download them from the website and then walk around and find the person you want to talk to. So let's make use of this opportunity to talk to the poster presenters as well. All right, we'll see you over there, and that will then also be the end of today after the poster session. So we will see you again in the Zoom webinar tomorrow morning at 11 o'clock Amsterdam time for the industry session.
Thank you. Bye-bye.
Bye.